why all you students must definitely watch this easy chapter of periodic table in order to avoid mistake which most of the students commit in their JEE and NEET examination because they do not revise it well. So this one shot will be actually a gunshot to give you all the relevant revision of that chapter. And personally, I have given it a name of periodic classification of elements because I have included all the relevant hydrogen, S block, P block basics in it also. So this chapter will be helping you as a foundation chapter for whole of your inorganic chemistry. Do not worry to write these lecture notes, and also you will be requiring a lot of questions to practice this side of chemistry. All of them you can definitely download for free from our PW app, the link to which is given in the description section. Because PW is the most loved organization by millions of students every year, which help them to excel in their competitive journey. So let us explore this side of inorganic chemistry. So the journey of inorganic chemistry starts with the existence of elements, and we know as of date from our periodic table there are 118 elements in nature. Sir, if we will study the property of each element, then we will go mad, we will go crazy because so many properties we have to learn them. That's why what our scientists, what our philosophers, what they did is they segregated all these elements and classified them so that if you know the property of one element, the property of the other can easily be at least predicted. And this gradual change in property when you move along the period and you move down the group is actually termed as periodicity, highly asked by JEE, even mains, even advanced, and even your board examinations. So this all thing starts with periodic table. Now, periodic table is what, as I've already told you, the arrangement of known elements, whatever elements you know, according to their properties. So this picture is just building up of elements which are of similar nature. But obviously, this picture was initiated by some beautiful minds. So out of respect also and out of chronology also, NCERT also gives you the detail that how development of periodic table came into being. Now, this first started from Lavoisier's classification, who simply said elements can either be metals, which have a tendency to donate or lose electron, giving nature, or they can be non-metals, that is, they have a tendency to accept or gain electrons, lalchi types. Now, when you give electron, you form a cation, and when you gain electron, you form an anion. Although gaining electron is not morally unethical as we humans know, but still, this is what Lavoisier classification was. But it was questioned because certain elements had both these properties. We very well know them, they are metalloids. So answering to this question, some other classification came. The next classification, although less known, is Prout's hypothesis. He just said that since hydrogen was the simplest atom, so he said you can synthesize every element from hydrogen, which we know as till date, this is practically not correct. Therefore, this classification was superseded by Dobereiner's triad. Now, what does Dobereiner triad said and did was he classified elements which had similar properties. How many elements he got as a group? Three elements, hence the name triad. Now, when he arranged them in increasing atomic mass, he found that the mass of middle element was the average of first and third, like in case of lithium, sodium, and potassium. There are many other examples of Dobereiner's triad like chlorine, bromine, iodine, but you do not have to remember each and every one of them. Although you may get a question that which of the following are Dobereiner triads or not. So I am giving a trick to learn that. Just take the difference between two, like bromine and chlorine has a difference of the difference in atomic number Z, not mass number. The difference is 18. Between bromine and iodine, the difference is also 18. So generally, a Dobereiner triad has elements whose difference between value of Z for first and second and for second and third is same, which can easily pick your answer. So you do not have to learn all these triads. But there was obviously some limitation, like These triad was completely not applicable for DNF block elements. For example, iron, cobalt, and nickel. This was named as a Dobereiner triad by Dobereiner itself, but this itself is not following this trend. That is, iron, cobalt, and nickel. If you arrange them, Dobereiner arranged them in a triad and said no, it is also a triad. But he was actually doing opposite of what he said. So these are some limitations because they were not following this tradition. So obviously some other classification was then further proposed, which was the Newland law of octaves. What Newland saw in nature, that Sat Sur, there are 7 notes of music. He must be an appreciator of music, good music. So he said, in nature, you can always have 7 notes. Similarly, you can only have 7 different type of elements, and every 8th element will have the property similar to that of the first one. Like from lithium to fluorine, 7 elements have different properties, but the next heavier element known at that point of time was sodium, and sodium property was similar to that of lithium. Similarly, magnesium was similar to that of beryllium. He thought, bingo, I have created something new. But this proposal was also valid till calcium, although some heavier elements from calcium was some of the heavier elements from calcium were also known, but they were not following the proposal given by Newland. So this was his limitation, that it was only valid till calcium. Moreover, noble gases were also not discovered at that point of time. If they would have been present, then after 7th element, the 8th heavier element would be neon, and neon do not have any property similar to that of lithium. So even if noble gases would have been discovered when Newland given this proposal, then his law of octaves would be law of non-naves. So obviously this was also later discarded and was superseded by this cylindrical and helix periodic table. Now, this classification is generally not given preference. What classification comes next is the Mendeleev's periodic table. But actually, the Mendeleev's periodic law is direct an outcome of this observation. The only difference is Mendeleev gave a periodic tabular form of this classification, whereas this logic drew this experimental cylinder. Sir, how this cylinder was drawn? You do not have to go into that basic, just understand this. That what he did is, he drew a helix shape. How he drew this helix shape? He mentioned elements in a cylinder. The cylinder was divided into 16 equal parts, and the helix that he came up with was drawn at an angle of 45 degree. Like this is drawn at an angle of 45 degree. And how drawn? By placing elements. And to his surprise, what he actually got is the elements which had similar property, like you find lithium over here, just perpendicular to lithium in the same line, he found sodium. So they were lying perpendicularly on the similar line. One more example, like he found boron over here, and just in the perpendicular line, he found, after boron, he should find, yes, aluminium. But obviously, since you can see, it is so tedious task to perform, but it was this cylindrical helix that gave a conclusion that the elements, if classified as per their increasing atomic mass, their properties, all the physical and chemical properties of these elements will be a periodic function of each other. So this was the table, but actually who used this? Mendeleev. What does Mendeleev said? Mendeleev law was, physical and chemical properties of elements are periodic function of their atomic masses. This logic actually initiated from there. Now, sir, you skipped one slide. Yes, Lother. What is Lother? After that cylindrical curve and before this Mendeleev's periodic table, there was in between one more development which further proved this thing, that no, physical and chemical properties of elements are definitely a function of their atomic masses, because atomic masses, the first graph which Lother drew was with atomic volume. Although practically speaking, Lother have taken several other physical properties, but this graph is one of the famous among them. So if what he observed is, when he drew this atomic volume with respect to atomic mass of whatever elements that were known at that point of time, he found a curve. And to this curve, now because this question is also has been many times asked by JEE. Sir, it is very difficult to remember. I'll make you remember one thing. You just go to the pattern. Top, white color, red, descending. From top, you descend, then you reach a bottom. So this green is the bottom. And after bottom, if you have to draw a curve, let's say you are drawing from the top, then you will descend, then you will reach bottom, and then you will ascend. These four places were occupied by some set of elements, and JEE used to ask this. So I'm giving a trick to remember. Top is occupied by group 1. So whenever this graph was peaking, group 1 is lithium, sodium, potassium. They were continuously coming to the top. So they were following a pattern. That means their physical and chemical properties are directly related to their atomic masses. In the descending side of the curve, whenever the curve was descending, what came? Group 2 elements came. In the bottom side of it, D block and metalloids came. And in the ascending side of it, halogens came. So I guess this will help you to remember, because must remember, given in NCERT, JEE always tricks you, and if you know these tricks, these answers will be quite easy for you to attempt. Moving ahead, as I've already discussed the initial law of Mendeleev's periodic table. So actually, what Mendeleev did was, through the study of his previous scientist, he inculcated all their logics and gave this law that the properties of elements are periodic function of their atomic masses. But because it was a tedious task to mark them out, so he made a table. And it was Mendeleev who gave the name that horizontal rows will now be named as periods. It was Mendeleev who named that vertical columns will now be named as groups. And when Mendeleev actually came up with this periodic table of Mendeleev, at that point of time, noble gases were not known. They were not known, and many of the elements were also not known. But this was the beauty of this Mendeleev's periodic table. Let us explore this. Sir, we have to read this periodic table also? Yes. Because directly question has in JEE mains, the question asking about this periodic table, I'll show you, also came. So we will also learn this table, but after the modern periodic table. So I'm just giving a brief about it first. So Mendeleev initially introduced 8 vertical columns called groups, and later, to account for other different elements, he subdivided these groups as AB. But this subdivision of AB was still 7th group. To 8th group, he further subdivided into 3. Similarly, initially he came up with 7 periods, those are horizontal rows. But later, he even subdivided these rows, but although not named AB, just increased the number of rows. So later, the number of rows became 10 in number. 7, 6, 7, 8, 9, and 10. Now, the beauty, the scientific Pandit stature of, because he predicted, he left some gap in the periodic table, and as the world, as the scientist, you go and you find element, you will find an element which I am naming X, which will have the property of these members. And later, when scientific community and researchers have gone out, they have found those elements with exact property and nature as predicted by Mendeleev. Similarly, when inert gases came into picture, when they were discovered, Newland law of octaves, obviously the octave should have been named nonave, so it was tremendously gone and blown. But here, to Mendeleev's periodic table, even discovery of noble gases didn't break the periodic table developed by Mendeleev, because they clearly fitted into this Mendeleev periodic table as the ninth group, to which he named zero group. We will be filling these elements, but after periodic table, because filling these elements was also loved by JEE. So before moving to modern periodic table, let us list some merits and demerits. So merits, obviously, Mendeleev periodic table made the study of elements, that their properties, the periodicity, much easy. He predicted new elements. NCERT used these two examples. Beneath aluminium and silicon, he placed a gap and named the element which you should discover later, which scientific community should discover later, and were discovered also. To the gap he named Eka aluminium and Eka silicon. The elements those were discovered were gallium and germanium. Some other elements he also predicted, although this is not there in NCERT, but you should remember, and I'm giving you mnemonics to remember. Studying is quite easy, but remembering them for longer period of time is difficult. So these mnemonics, you build a story around it, will definitely help you. I will not personally write those mnemonics because they could offend some audience, because we are on a national, maybe international platform. So I'm not writing those mnemonics. So this is your religious responsibility to pick up your pen and write those mnemonics and then build a story around it so that you remember it for longer period of time. So other predicted elements are Ganga se Jamuna tak. Ganga se Jamuna tak. PM atke. Ganga se Jamuna tak. PM atke. I hope you wrote it. As in gallium, scandium, germanium, technetium. PM is promethium and astatine. These were elements where gap was introduced, and later these were found as with properties as predicted by Mendeleev. Again, he also did some correction with the atomic weights of the elements. Whose atomic weights he corrected? Again, a mnemonic, a rhyme, write it down. You, not you, mnemonic, you, Beman insan. What does Beman insan? As in a person who is not true. You, Beman insan. What does Beman insan do? Churao, steal gold. Gold, and if you steal gold, I will pitunga. So you बेमान इंसान गोल्ड चुरा लिया, now you पीटूंगा. So you बेमान इंसान AUPT. These are all just rhymes. And now coming to the point, how these masses were rectified. Remember mole concept. How can you relate atomic weight of species? Sir, molecular mass is equal to equivalent mass, their equivalent weight into their valency factor. I hope you remember this through redox chapter of ours. Initially, because beryllium example is most famous for this, initially people thought atomic mass of beryllium was somewhere around 13.5. Why? Because what is equivalent weight? I'm giving an example for beryllium. What is equivalent weight? Equivalent weight of beryllium is 4.5. Sir, at least tell us again what is equivalent weight. Equivalent weight is technically, statistically, whatever weight of you, if you are an element, your weight will be combining with weight of oxygen. So whatever is your weight that can combine with 8 gram of oxygen will be termed as your equivalent weight. So what weight of beryllium was required to react with 8 gram of oxygen? 4.5 gram. So initially, before Mendeleev, people incorrectly assumed this was incorrect. People incorrectly assumed that valency factor for beryllium was 3, and therefore they incorrectly found the atomic weight to be 13.5. Actually, Mendeleev suggested no, because beryllium was having properties similar to that of magnesium, calcium, which had an oxidation state of 2. So he said no, the valency factor of beryllium will be 2. He corrected this, and Therefore, the atomic mass was also corrected, and corrected value came out to be 9U for an atom and 9 gram for 1 mole of atom. So these are some merits of Mendeleev's periodic table. Moving forward and coming to some demerits, because we know now long form of periodic table exists, so Mendeleev table is not completely true. Now, obviously, the first demerit is the position of hydrogen. Hydrogen was having properties similar to that of alkali metals also, which is now present in group 1 only, and with halogens also. So its position was always doubted and the doubt came to Mendeleev. He could not give an answer, a satisfactory answer. Position of isotopes, for example, you are placing hydrogen as in with mass number 1. With hydrogen, I'm taking isotopes. With mass number 2, deuterium. Hydrogen with mass number 3, tritium. So what can you comment? The people ask Mendeleev, what can you comment about them? Because if you consider H3, tritium, then it may find some different atomic, because of its mass, its place may be replaced. So which isotope we will use? He cannot comment on that. Failed. Some anomalous pair. Mendeleev made his periodic table on increasing atomic mass, but there were certain pairs, again, you should learn them. What are these pairs? These 4 pairs. What Mendeleev did was, example, argon and potassium, which is heavier. Argon has a mass of 39.9. Potassium has a mass of 39.1. So actually potassium should be before argon, but no, Mendeleev did the opposite. Why? Because argon property must be matching with the elements of its group, and potassium is matching with elements of its group. So he sometimes placed lighter element later and heavier element before. These are the 4 famous examples. Sir, rhyme? Yes, write them down. RK, Ranbir Kapoor, grandfather Rishi Kapoor, his grandfather is Raj Kapoor. Raj Kapoor Stadium is still there in Mumbai, called RK Studios. So RK Company, RK Company as in cobalt nickel. If you go to that famous company, you will get tea and ice cream. You will get tea, ice cream, and you will also get thanda pani. Thanda pani. Now, what are these elements? Argon, potassium, cobalt, nickel, the pair, tellurium and iodine. pH is thorium. Pa is protactinium. So these are the 4 pairs which were placed as heavier was placed before and lighter was placed after. Why? Because they were matching to the properties of the group. That means at least group members will have similar property? No. Unlike elements were also placed in same group. Like in his first group, he subdivided into A and B. First subdivision in A part, in A column, alkali metals came: lithium, sodium, potassium, very reactive. And in subcolumn B, coinage metal, noble metals, copper, silver, gold. People asked if you are placing them because group properties must be same. They are lying on same group and have no relation in their properties. People started asking and doubting this also. Similarly, like, at least whatever elements who are like, they should be placed together. So like elements were placed in different groups. For example, we will make that periodic table for you. In modern periodic table, you have these noble metals. What are the noble metals? Gold, silver and platinum. So platinum he placed somewhere else and gold, silver he placed together. So people ask, if they are noble metals, at least place them together. So these were all the unsuccessful results of Mendeleev. The last one is, this drawback is still now valid, position of lanthanides and actinides. Still in the modern periodic table, we have created a separate group problem, which is F block. So their position were not clear at that point of time also. And today, in this, till this date also, they are given a separate F block beneath your periodic table. So sir, after so many limitation, at least come to Henry, the modern periodic table. Actually, Moseley was not a chemist. He was a physicist. He was doing some bombardment of electrons. High bombardment is giving high velocity, but he was bombarding using electrons and bombarding metals to the surface. He was doing some experiment related to his physics. He was a X-ray. He was a physicist. So whenever high frequency electromagnetic radiation as in electrons are bombarded to a metal, we know that through atomic structure X-rays are produced. So these produced X-rays, he was experimenting and statistically making graphs that how they are related. So the characteristic frequency of the X-ray released by metals, that characteristic frequency, its under root was having a straight line relationship not with atomic mass but with atomic number. A very famous result which says under root of frequency is equal to some constant whole into z minus b. A very famous formula. Actually, this was his graphical representation which shows that atomic number has a direct relationship with the properties of elements, and therefore till today, what is the classification law? The periodic and the physical and chemical properties of every element are periodic function of their atomic number, not their mass number. And because of this, we have landed up to our periodic table. So you should at least make it once and we will discuss it to a greater extent. So now, after having a quick view of the modern periodic table, let us directly jump to the not learning, not cramming part of it, but the technical part of it. We must have read the atomic structure before. If you have not seen that, go and watch atomic structure first. Definitely will make 2 questions in JEE and will also help in getting a foundation. People say Moseley did experiment and said the periodic table is a periodic, the elements arrangement is a periodic function of their atomic number. But actually, it is directly in sync with the Aufbau and the electronic configuration proposed by the quantum mechanical model. How, sir? I'll tell you. So therefore, I've given you a brief view of that modern periodic table and directly jumping into it. Now, to the period number, I'm marking n, which is the n of our atomic structure, the principal quantum number n. So you just think of this period number as the principal quantum number and tell me which, as per Aufbau rule and electronic configuration, which orbital, which shell and subshell filled first? Sir, S subshell. So therefore, how many orbitals you have? 4, because how many blocks we have in this modern periodic table? 4, because basically how many orbitals, subshells we have used? 4. The S subshell with 1 orbital filling 2 electrons, so 2 groups. The P subshell having 3 degenerate orbitals, and hence according to Pauli 2 electron can come in each, so 6 groups. The D1 will have 5 subshells, hence 7 groups. The F subshell 7 orbitals, hence 14 groups. Now coming to, because these questions are directly asked, I'll show you. What subshell is filled first? 1s. How many? Hydrogen and helium, 2 electrons. So what filled at the very first, sir? 1s. 1, the period number, and s, hydrogen and helium. So as in 1s1 and 1s2, I'm writing for the case of simplicity that in period 1, 2 are filled. So how many elements we have filled in the first row? 2. I'm referring to these number as magic number. We'll see what magic they do. Now, Aufbau says after 1s, what subshell gets filled? 2s. So 2s2, therefore 2 elements, lithium and beryllium. Leave this because D block come into existence in periodic table also post 4th period. I mean post 3rd period in 4th period. So there is no 2D or 2P type of thing. There is no 2D, but yes, 2P will exist. How many 2P will be filled from 1 to 6? From 1 till 6. From boron till the last, which is neon. What is its atomic number? 10. How can you get its atomic number directly? How many elements you filled? 8. So what will be atomic number of last element? Sir, 2 plus 8, 10. That is what magic number do. It gives you the atomic number directly. So 2 plus 8 is 10. So 10 will be the atomic number of last 18th group element, neon in this case. After that, what gets filled? Sir, 3s. So 3s2, 2 elements of S block. Still, after 3s, what filled? 3d. No, sir, 3p. So therefore, no D till third period. So 1 to 6. Okay, I'm sorry. This is okay, third period. So 3p, 1 to 6, perfect. How many again elements you filled? 8. So what magic numbers are doing? 10 plus 8 is 18. So atomic number of last, that is argon, is 18th. Now, from above says after 3p, what's get filled? 4s. After 4s, what gets filled? Sir, 3d. The first time D comes into electronic configuration filling is 3D. So here also in periodic table also, the D block that we will be introducing, it will be introduced from fourth period. So just an observational thing. S and P has the same electronic configuration principal quantum number as the period number. So we say for S and P, for S block, we say they have a general electronic configuration of NS, either 1 or 2. For 1 or 2, what are S block elements whose last electron goes to S subshell? So what will be P block elements whose last electron will go to P subshell? What will be their general valence electronic configuration? Valence is outermost. Sir, their outermost is this nth shell. So for P block, NS2 must be filled. These two has to be filled. Then you will come to P. So for P block, it will be 1 to 6. Why N? Because the period number for S and P are same. But for D, period number is 4. But what principal quantum number is getting filled? 3D. So therefore, we say for D block elements, if you need to fill them, obviously they should be filled. So NS must be filled. And after that, what gets filled? After that, N-1 D gets filled. Sir, why you have not filled? Because we know there are some in D block, we will be discussing them separately, that like in case of chromium and copper, we have done in atomic structure. So I'm again telling you, in case of chromium and copper, what happens is one electron from 4s migrates inside to make the N-1, the inner shell. This is valence shell, this is inner shell. Just inside the inner shell is also known as penultimate shell. So this penultimate shell sometimes get 10 electrons like in chromium and copper. So therefore, I'm writing as 0 to 2 because they are not always 2. They can be 1 also. And in D block, you will see it can be 0 also. We'll see. So this will be its electronic configuration. What will be number of electrons that D can have from 1 to 10? Scandium will have 1. Rest keep on increasing. It will be gaining electrons in the D subshell. Now, similarly, for F block, can you... first, let us reach to F block. This is 3D. Then what? P? 4P. Why 4P? Because S and P, the valence electron will have same principal quantum number as the period number. So, sir, this is 5s2. Then N-1 as in 4D, 1 to 10. Here also 1 to 10. This P is 5P. It will be filled from 1 to 6. Moving ahead, this is 6S. Now, in the sixth period, go to your Aufbau rule. After 6S, what's the N plus L rule? After 6S, what's get filled? The first time F gets lesser energy and gets filled. Which F? So 4F. So, if period number is 6, what principal quantum number we are using? 4. So, can you tell me if NS, the principal quantum number is with N, D takes 1 lesser than principal quantum number, F takes 2 lesser than, because we are filling how much over here? Sir, we are filling which or subshell over here? Sir, 4F. Now, one atomic structure common sense and periodic table will also help you in that. After 6s2, what filled? Next is 5d, but lanthanum will be 5d1. Sir, but you said after 6s, 4f must be filled. But after 6s, 4f must be filled, but in order to come in sync with the elements, actually lanthanium is filled first, and the electronic configuration which scientist community has ended up with is, they say, because lanthanum is a D block element, because it's coming in the D subshell, in the D block. So D subshell will be filled. So what will be the electronic configuration of lanthanum? This 57th electron is filled in 5d1. And after, so lanthanum is actually a D block element, but its property is related to lanthanoids, that is the element that will be coming after this, and there 4f is filled from 1 till 14. So after this, what will be atomic number of next element? 72, because from 58 to 71 lanthanoids are filled. So after 71, the next number is 72. 72 is filled where? Again in the D block. So it's like, if it is 5d1, then this 72nd will be 5d2. So this you have to keep in mind while making electronic configurations. So after this, what is filled, sir? 6p, 1 to 6. Again repeat the same task. First filled is 7s2. Next, sir, this actinium 1, which is 6d1. After 6d1, that is after atomic number 89, next from 90 till 103, there are 14 elements. They are filled in 5f, 1 to 14. Then after 103, 104 gets filled just beneath 72nd element atomic number. And this will be 6d2. Then further 6d till 10. Here also till 10. And then at last what is filled? 7p, 1 to 6. So this accordance is directly in sync with the quantum mechanical model. So I am again telling you what this magic number do for us. Okay. So how many elements we have filled in fourth period? Sir, up this 6, this 2, 8 plus extra 10. So there are filling of 18 electrons. So what will be atomic number of last element? 18 plus 18 is 36. After that, how many are filled, sir? 18 only. So 36 and 18 becomes 54. So last element will have an atomic number of 54. Now remember, fifth period, last element atomic number is 54. The magic number, magic. After 54, S6S2, 54, 55, 56. Then this 57 of lanthanum you can even predict with this periodic table. Now, because 14 extra are filled in this F block element which is inside of this D, hence this D block contains inside this D block, this F are also filled. So this F block is also termed as inner transition element, because S and P are representative elements, the main elements which represents the property of most element found in nature, and D elements are termed as transition elements, and F block elements are termed as inner transition elements because they comes after lanthanium and actinium. Now, so again the magic number part, sir, because 14 are extra added, so 18 plus 14 becomes 32. Sir, if 32 added, what will be atomic number of last electron? 54 plus 32 becomes 86. So 86 will be atomic number of last element of sixth period, 18th group. After 86, sir, S2, S block, 87, 88. So this 89 actinium atomic number I can predict. After this 89, 14 will go to F block from 90 till 103. The next 104 will come next to actinium. Now, this is the perfect sync. Okay, so at last I'm again having 32. So what will be the atomic number of last known element? 118. Now, sir, electronic configuration, so we will know, and we will see in questions also how this knowledge will be greatly used by you. You do not have to mug all these things up. These are all just common sense in accordance with quantum mechanical model electronic configuration. Now, sir, we can definitely tell, if you give us an atomic number, we can directly tell what is its group number, period number, and block. How? The magic numbers. We know 2, 8, 8, 18, 18, 32, 32. We'll practice a question that how we are using it. You'll find a question, a mains question we'll be finding. But I'm just putting things together. So these are all electronic configuration as per modern theory, as per modern periodic table, and in accordance with atomic structure. But sir, what all elements also we should learn? JEE is in love with you knowing the elements, atomic number and symbol. Mind you, atomic number and symbol, their name as such you cannot mug up at this point of time. If you have learned them before, good for you. But all those of my students over there who are just starting and gaining something for JEE, so I suggest you can leave the name. You have to learn the atomic number. Atomic number I've helped you with. Now the symbol. For symbol, I'm giving you some mnemonics, but let us first go over here only, because some mnemonics we know. For those of you who do not know, I'm not writing those mnemonics for you because they are very famous. But if you are not aware of anything starting from zero, you can write down. I'm uttering them. Now, sir, we have filled this electronic periodic table. Period 1, 1s2, hydrogen, helium. Period 2, lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, neon. Reached till atomic number 10. Now, period 3, sodium, magnesium, this is 3s2. Then 3p6, 3p1, 2, 6, reached till 18. Next is 4s2 till calcium, 4th period. Then this is starting of D block, n-1, so 4s2, so this will be 3d1. Similarly, last will be 3d10, 10 filled. Now, after calcium, I want you to learn a rhyme. What is the rhyme? Shakti Walker. I'm just reading the symbol but rhyming it. So you can write that down also. Shakti Walker, as in Johnny Walker, Shakti Kapoor. So Shakti Walker. Man fe ko ni. You have a heart, you throw that heart. Man fe ko ni. And when you throw something, that thing gets swelled. So Sujan, you hit me, I get swelled over here. In Hindi, it is called Sujan. So Shakti Walker, man te ko ni Sujan. This is the rhyme I use. If you already know a rhyme, go by your story and rhyme. I'm just giving a rhyme for all those who are not in sync with any rhyme. So Shakti Walker, man fe ko ni Sujan. I have repeated it 3 times. I hope you must have written it. So this is still atomic number 30. I want you to learn atomic number 30 like this only, with no rhyme from 21 till 30. Until calcium, we have just used known elements. So you should read them few times. Of till 20, you must be knowing without any rhyme. Now, sir, can you tell us rhyme of S block? Yes. है ली ना की रब से फरियाद, as in hydrogen, lithium, sodium, potassium, rubidium, cesium, francium. I'm again telling you, name you can let go. Name you can let go for mains, but symbol and atomic number. Sir, how will I know their atomic number? Like for example, if I would need to know atomic number of francium, how can I know it? I know it is first group, 7th period. So go to the magic numbers. What is atomic number of this last element? Sir, 86. 6th period, last element. Have you seen them? Yes. It's a 6th period, last element 86. So these magic number you can always count the atomic number of last element of that corresponding period. What are the magic numbers? 2, 8, 8, 18, 18, 32, 32. So if I know 86 is 6th period, last element, so I need to calculate FR. Okay, I'm sorry. I need to calculate this FR. So this FR will be 86 plus 1, that is 87. Similarly, you can get adding those number of 1 unit of proton and get to whatever element is asked in the question. We'll see such questions also. Now, group 2 rhyme. Beta mange car scooter baap razi. Again, beta mange car scooter baap razi. Now, P block, boron family. Why P block? Because the last electron is going in P subshell. Baigan, aloo, gajar in thela. Radioactive, not required. Next, Kashi, Gaye, Shankar, Parvati. As in carbon, silicon, germanium, tin and lead. Very famous. New Zealand, Pakistan, Australia. Sab Bikau. I am not writing it. I mean, this is just for remembering. New Zealand, Pakistan, Australia, sab Bikau. Nitrogen, phosphorus, arsenic, antimony, bismuth. Us se tipo. Oxygen, sulfur, selenium, tellurium, polonium. Fluorine, chlorine, bromine, iodine, astatine, the famous halogens. And the last, inert gases, hai, na, agarkar. In our times, there was a player, Ajit Agarkar. So, if I'm giving you a rhyme, you can relate or you can find some other. Hai, but if you know some rhyme, go by it. If not, then go by whatever rhyme I'm giving you. Write it down. Hai, na, Agarkar. I say Argar. His name was Ajit Agarkar, but why do I say I pronounce Argar so that I may come with that R? Hai, na, Agarkar, 0, run pe. As in helium, neon, argon, krypton, xenon and radon. Now, these are some elements which we know through this rhyme and the structure we can make. I'll take you to that structure, that whatever elements we have made. This much elements we have made. How much? Till atomic number 30 of zinc. And after that we know the rhyme for P blocks. Hai, na, argar, kar, 0, run pe. So these are all elements which I have shown you over there, but these all rhymes we know. What else we know? Sir, we know in 6th period after barium, lanthanum comes with atomic number 57. What we know in 7th period after radium, actinium comes and followed by the lanthanoids and actinoids. This we have done. So I have made a simple picture for you. Now, some other elements I want you to remember with whatever rhyme we have done, with rhyme we have drawn this much. Now, zinc, cadmium, mercury are grouped together because they are called the volatile metals of D block elements. Among D block element, they are almost most volatile. So this is a property also which you should remember. Hence, remember them as a unit. What is the unit? Zinc, cadmium, mercury. So go with the flow. Zinc, cadmium, mercury. Then the coinage metals, which are copper, silver, gold. They were used for making coins, although we know they are generally the noble metals also. Although platinum is also noble metal. Actually, noble metal is copper, not copper. Silver, gold and platinum are basically noble metals. Now, beneath nickel, this confuses my students a lot. So I have made a trick. Beneath nickel, you get PDPT. Some people, my students used to forget this a lot. So what I have done a trick is, beneath nickel, you first have to remember PP. Beneath nickel, platinum, palladium is there. But what people misses is which is first. PDPT is there, but PD or PT, which comes first? Alphabetically, what comes first? D or T? D. So nickel, PD, because alphabetically D comes first, and then PT. They also have some different electronic configuration, but that we will separately deal when we will study D block. Because as promised, I said S and P blocks basic will be included in periodic table and the chemical bonding that will be coming. But for D blocks and coordination, because JEE is in love with them more, so for those topics we will be doing separate chapters for D block and coordination. Now, these all elements we should learn, we should know, are known. Coming back, so if we know these all elements, what we can do is, sir, what about the remaining, like this is a 3D series, this is 4D series, this is 5D series. 3D series we learnt, Shakti Walker, Man Fekoni, Sujan. That 4D and 5D we do not have any rhyme. Lanthanoids and actinoids we do not have any rhyme, giving you a rhyme for them. Because actually, but questions relating to rhymes of D and F block element will be dealt in separately D and F block chapter. But you should know these rhymes also, because many a times, although less in number, but many a times questions were not being solved if you do not know the symbol associated with atomic number. Because electronic configuration, you can always predict through this. If you know atomic number, you will get to know which block, which group, which period it belongs. And if you know that, you can easily make out the electronic configuration as per the Aufbau rule. We have just collaborated with periodic table. So what else you need is the symbol. So for symbol, I am giving you a rhyme. First, I have written this rhyme for you, but I am first telling you what are these elements. I'm iterating that rhyme over here. Then I have written that rhyme also. That rhyme I have written. Although till here I have not written that rhyme, I have iterated it, but that rhyme I have written because many of my students do not learn that rhyme. So I have given this rhyme for you so that you do not have to write it. Just read it regularly. I mean, it will hardly take 2 to 3 minutes, but you have to keep reading them regularly. It will always come in sync with you. Now, so coming to the 4D series is yttrium. Although you can skip the name, symbol is important. Yttrium, zirconium. What is the rhyme? Yari zara si nibha. Keep writing it. I'll be repeating it once. Yari zara si nibha maut tak रुकावट राह में पड़ी है. Although this padi, silver, cadmium, we already know. Zinc, cadmium, mercury, copper, silver, gold, nickel, PDPT. So I just need rhyme till here. I, as in if you are learning like I'm telling you, you just have to read till here. Raha. So what is the rhyme? Yari zara si nibha maut tak rukawat raha. Rest we know. Now, for lanthan, for 5D series, what is the rhyme? La hafta varna re usdhar irdhar. Why do I say irdhar? Because this is idiom, IR. So udhar irdhar. La hafta varna re usdhar irdhar. Pitunga we do not need, because this we already know through our symmetry of elements that we have drawn. Now, for this last 6D series, what rhyme I use? AC actinium we know. Now this is a personal rhyme. You will not find this rhyme anywhere. I have made it. Raftar, the singer. Raftar dubbing singing बहुत हंस के करता है. Raftar, the singer, he does dubbing and singing, SG, बहुत, BH, हंस के, with a delight. mat des, do not give him mat des. In the northern side of India, in my home, in my village, in my town, the people say, if you want them to do not give anything to them, they mat des. So mat des. Rigged cones. Actually, in order to certain musicians, they take cones for playing tabla type of thing. So rigged cones, RG. That's the rhyme. Again, रफ्तार डबिंग सिंगिंग बहुत हंस के करता है. मत देश, डोंट गिव rugged or rigged cones. Anyway, you just have to remember RG. So rugged, rigged, whatever. Rigged cones, CN. Now, for lanthanides, what rhyme I have is Sina par Nadia PM ki samai. I'm in love with PM. So, Sina par Nadia PM ki samai. यूं गद गद तब दिल ये हुआ एचओ. अरे ER तुम TM ये भी लूट लो YBLU. These are the rhyme for lanthanoids. For actinoids, थोड़े पहलवान उनसे निपटेंगे NP. पुराने आम कम बिकेंगे BK. कैफे में ऐसे फरमाओ CF ES फरमाओ FM. मैडम MD. Noble NO. Laure. Do you bring on Nobel Prize? Sir, how it is getting related? I'm telling you a story. CF and ES, कैफे में ऐसे फरमाओ. CF is Californium while ES is Einsteinium and FM is Fermium. So Fermi layer named by a scientist. ES Einstein, that name you also have to learn. So Einstein, Fermi, I mean, if you think of such great scientists, Nobel Prize will come into your mind. So Madam MD, Nobel Prize, Laure. Why Ray? Because LR. Now, sir, you have said that rhyme, but we cannot remember them. That's why I have given you these rhymes. Where, see, this is what I have done while writing the rhyme is, I have written rhyme also. Like for, this was a clear-cut rhyme that you have to remember. Shakti, Walker, Man, Fe, Ko, Ni, Sujan. So this 3D series is easy. 4D series started from Y, ending till CD. We need rhyme till RH because over there we know the element through symmetry. Zinc, cadmium, mercury, copper, silver, gold. Acha, silver, gold also people misses. So who is cheaper, silver or gold? Silver. So cheaper, expensive. Then PDPT if you miss, P you will remember, I'm telling you. You will miss whether D is up or T is up. So D comes first, so PDPT. So till here we know. So we need rhyme before this. Now, Yari zara si, see, Yari, here I have written the rhyme. Yari zara si nibha maut tak rukavat rah mein padi. You do not need, but rukavat rah mein. And for the rhyme, what alphabets you have to use for the symbol? Rah, RH, green colored, RH. Rukavat, RU, RU. Now, I have written name also. RH is rhodium. RU is ruthenium. TC, tak, TC, TC, technetium. Moth, MO is molybdenum. Now, NB is niobium. ZR is zirconium. Y is yttrium. Although I have written the names also, but I am suggesting if you are doing it just for mains, then you should leave the name, but you should learn the symbol so that you can relate this symbol with atomic number. Atomic number, how will you find? Through the Aufbau rule, link, and friendship with periodic table of hours. And the element, the symbol that is coming into that position of periodic table, for that you have to remember this rhyme. Now, again, the rhyme for after lanthanum, which I have given you, La hafta varna re usdar idhar pitunga. So rhyme you have not written because this is easy. Because this is easy. What is easy about it? La hafta, as in you are a criminal. If you are not, I'm building a story. So you go to people and ask for money. So la hafta. If somebody will not give you money, then varna re, you are giving dhamki. You are threatening the person. Kya? Usdhar irdhar. Why irdhar? Because it is IR. Pitunga. You do not need rhyme because you know element by symmetry. Now here you again need rhyme. This rhyme I have told you. रफ्तार डबिंग सिंगिंग बहुत हंस के करता है. मत देश MTDS मत देश rigged cones. Or in there is one more rhyme which is famous. अच्छा RD शर्मा की बुक में हैं मैथ्स के डिफिकल्ट रेंज के कोन्स या क्वेश्चंस. So I prefer this because I can directly go into the symbol of the element. So I've given you written this also and that also. Now, sir, what about lanthanoids and actinoids? Written. Lanthanoids, सीना पार नदिया प्रेम की समाई, यूं गदगद तब दिल ये हुआ, अरे तुम ये भी लूट लो. The rhyme also I have written in green color, and the symbol which you have to extract from the rhyme is written as red colors symbol. Name you can skip for now. If you or else I have written names also. Now, actinoids, थोड़े पहलवान उनसे निपटेंगे. 4 rhyme finished in this 4, so made this yellow block. पुराने आम कम बिकेंगे, again a block. कैफे में ऐसे फरमाओ, because who are Fermat and ऐसे? Einstein and Fermium. Fermium as in Fermi-Layer, related to scientists, so directly come Madam, Nobel, Laure. MD, NO, R. Lau, Ray. That's why I'm focusing on Ray, because this is LR. LR is Laurentium. So these elements, sir, you have made us learn so much. Do it. Given you that also, sir. But why? What help it will provide us? Now, attempt this question and tell me whether that was useful or not. So you can clearly see with this match the column that why I said periodic table is such an easy yet scoring chapter. Now, you have to match these columns. Just by looking at the options, I mean, it is quite evident to you that the first option, P is 3, 2, 4 or 1. So you just look at P and you will get your answer. What is P? Sir, nitrogen. Nitrogen has electronic configuration of nitrogen family has outermost electrons as in 5. So it will be some NS2, NP3. And what N? Second period, it belongs to second period. So 2s2, 2p3. So this is 3, bingo. You will take, but we are learning, so doing everything or else answer is done. Now, sulfur, sir, oxygen family. What is oxygen family? Oxygen family is NS2, NP4. So NS2, NP4, I have, yes, 3s2, 3p4 because sulfur is third period element. So Q is S, N is 3, so this is correct. Obviously, I got my answer, but just checking. Q is 2, right? What about R? Bromine. What electronic configuration bromine has? 7 electrons. So NS2, NP5. NS2, NP5. Acha. Is it fourth period element bromine? Sir, fluorine, second period. Fluorine, chlorine, bromine. Yes, sir, it's fourth period. So that electronic configuration in mind will always help you. Now, krypton. So, sir, inert gas. है ना अगर कर. So this is also inert gas. Inert gas is NS2, NP6. Sir, this is the way you just get your answer. Moving ahead. Now, sir, but we have done so many. Listen, I'm telling you one thing now. The periodic table which I made, leaving behind the 3D, you should know 4D, 5D and lanthanoids and actinoids. Those elements and those rhyme will only help you for D and F block elements, because over there we will see when we will discuss D and F block elements that in order to predict their oxidation states, whether they will show that oxidation state or not. So various questions comes because if you know their symbol and their atomic number, but most of the time their atomic number are also given in question. If not, then you should know that. So if you are having good amount of time, then you can invest in learning that rhymes of 5D, 6D, lanthanoids, actinoids, or else you can skip also. Coming over here again. Now, this again, you are having a match the column. These are all PYQs. I'm just discussing those questions. That will be helping you directly. So 37, sir, magic numbers we know. What are them? Just revise it, or just let us revise them. Sir, 2, 8, 8, 18, 18, 32, 32. Almost this much is not required. Second period element, last element has atomic number 10. Then 18, 18, 18 is 36. Then 54. Then 86. You just remember these elements, these atomic number also of the last element, that is of inert gas. How will help you? I'll tell you. 37. So 36 is of inert gas. So 37 is just add 1. So after group 18, where will you reach? Adding one S block. So 37 is definitely an S block element. So 37 as in P is an S block element as in 4. So P is 4. No, no. You may also be right. You may also be right. Let us check more. Now see other option. You are landed up with two options. So Q is 3, Q is 2, R is 2, R is 1, S is something, S is something. So you just do any one and you will get your answer. So just let us see which is closest to inert gas. 78, 52, because I have 54. So 54, 2 units, I mean 2 groups prior. So 18th group, no. Halogen, no. Oxygen family. So oxygen family is a P block element. So 52 is a P block element. P block element as in 1. So R is definitely 1. R is definitely 1. R is definitely 1. D is your answer. D is your answer. So you can very well do this. Again, 65. How will you, where will you land, sir? 54, between 54 and 86. 54 is which period? So period 1. All this question is done. But if at all only this is asked, then how can you count 52? So this is just for your practice. Question is done. Period number 1, 2, 3, 4, 5. Okay, sir. If I'm talking of, let's say 65. So 65 will be a period number 6 element. Why? Because it is more than 54, less than 86. So it is definitely a 6th period element. Now, I have to go till 65. So this 65 will belong to which block? Let us check. Now, 65. 54 we reach. So after 54, 6th period. 6s2. So 54 plus 2 is, I have reached till 56. Then, sir, lanthanum. That is 5d1, 57. After this 57, F block will be filled. From 58 till 71. 57 plus 14 is 71. So, sir, it will be an F block element. So that's why this 58, 71 also I have written. So those conclusions, if you will keep in your mind, it will make your answer faster. So obviously 65 is an F block element. So S is an F block element. S is 3. Yes, S is 3. Now 78, sir, 78 till 71 I'm going to F block. After this 9 will be filled in D block. 9 as in from 70 to 71 plus 9 is 71 plus 9 is 80. So till 80 it will be filled in D block. What is it saying? 78. So it's a D block element. As in Q is 2. Q is 2. So you can check any. Although this question was easy, but you should know how to do each and every group identification, period identification. Magic numbers and the common sense of electronic configuration via quantum theory will help you. Proved. Moving ahead. 120 not yet discovered. Again a mains question. 120 not yet discovered. What will be its? What will be its? Okay. What type of metal it is? Sir, 118 is 18th group. So 119, 120. So it will be an alkaline earth metal. S block, alkaline earth metal. Moving ahead. Now, the number, I have just taken few questions. You will get a lot of questions of this sort and they are repeatedly coming. So giving you the basic. Now, group number of valence electron and valency. Okay, now what is valency? You know from class 9. Valency is the combining capacity of an atom. What is your combining capacity? It may be equal to number of valence electrons, or if you are reaching the stable octet or inert configuration, then you have a capacity of, let's say, sharing more electrons, but if you are reaching stability, you will not share that many electrons. For example, oxygen family has number of electrons equal to 6, NS2, NP4. So their combining capacity is 6, but sometimes they may not use all of their capacity, because if they are getting stable by just using 2 of their valence electron, so their combining capacity can be 2 also. Because out of those 6, if only 2 electrons are shared, the octet gets complete, the electronic configuration gets stable. And why an atom reacts with another atom? To get stable. So valency is the combining capacity of any atom or any element which make them acquire stable configuration. So Combining capacity to acquire stable configuration is valency. Now, although this question is very simple because 15, we do not. That's why I told you till 20 you should know without any rhyme. 15 is, sir, 15 is phosphorus. Phosphorus is nitrogen family. Nitrogen family is group 15. So group 15, no, no. You may be right, you may be right. Valence electron, nitrogen family has how many valence electrons? 5. NS2, NP3, 5. So answer is C. But valencies, I have 5. But if I combine only with 3, I will attain inert configuration. So why will I require more valence electrons? I may use, but probably current always flows in that direction where resistance is least. So if I have 5 electrons, I may only use 3. So my valency will be definitely 3. It may go beyond 3, that we'll see in chemical bonding. Now, again, 2020 question, set of numbers, transition elements. Transition element starts from scandium, atomic number 21. So before 20, you cannot find transition elements. So option C gone because there's 9. 21 accepted, 21 accepted. So these two are probable answers for us. What about this? Because it's a mains question, although you can check the first, only you can check. 36 is inert gas, so 37 is definitely an S block. The question is saying it contains only transition. So it should not contain any, it should only contain transition as in D block. Because it is an S block, so it is also gone. So you are left with two options, 21, 21, correct. 25, correct. 32. Sir, 32. 36 is inert gas. So 36, 35, 34, 33, sir, 32 will definitely be a P block element. Moreover, you learn also from scandium till zinc is D block, zinc is 30. So 31, 32 will definitely be P block. So because it is P block, it is also gone. This is your answer. Sir, what about 42, 72? You can always check using magic numbers, but that will take time. So that's a task for you, homework for you. So answer is, I've already given B. Now, one more question, choose the correct option which has D10 configuration. This also we know through atomic structure. D10 configuration, who has the last D block group, the volatile metals which are zinc, cadmium and mercury. But through atomic structure, we know this also, that coinage, copper, silver, gold coinage also acquire 1 electron from the S subshell. So this acquires also N-1 D10 configuration, these coinage. So where are you served these? So nickel do not, nickel do not, nickel do not. So this is your answer. These are the basic beauty of inorganic chemistry, that you see the question, tick the answer, move ahead. Now, this was also loved by JEE. Why I am saying you should not very seriously devote your time in learning symbols, the rhyme that I've done. Reason being, if you learn those symbols, science community has given an IUPAC for inorganic elements also. What is that? They have given numbers to, and they even say that after 100, you should use this nomenclature instead of the symbol name. What is it? You know the atomic number. They are giving name to each digit. 0, they call nil. 1, un. 2, bi. 3, tri. 4, quad. 5, pent. 6, hex. 7, organic, we say hept, but here it is sept. 8, oct, and 9, ENN. How will you write them? Just write these digits, and after the end of that digit, just write the name of the digits. If generally it is used after 100, so there must be 3 digits. So write these 3 digits corresponding name plus suffix it with IUM, because generally they are after 100, they are transition and inner transition metals. So generally metal IUPAC says it should be suffixed with an IUM. The question comes, many question comes, I've just given few. 2022 question, IUPAC nomenclature, you have to tell of element with this configuration. Sir, how to know atomic number? Again, go to that basic. What basic, sir? Rn. What is Rn? Sir, hai na agar kar 0 run pe. As in 2, 4, 6. This is 6th period. So 6th period is gone. We have to fill the 7th period. This I know. How 7th period is filled? First 7s2, 7s2. Why written opposite? Because generally you fill according to Aufbau rule, but the inner shell can be written first and outer shell can be written later, like over here. So 6s2 filled, then actinium 61 filled, then 5f14. Okay, so this is the last element of lanthanoids, actinoids. Remember, actinium is 89. So from 90 till 103, add it 103. So your atomic number is 103. Again, because we have done that periodic table, it will come in a Ziffy. So at least invest time with that. 103. Now name 103. 1 is un. All options are right. 0 is nil. All options are right. 3 is tri. No, this is 1. Tri, yes, this is 3. Quad, it is 4. Bi, this is 2. So we landed up with this. After tri, you add IUM. So why there are not double I? Because obviously when you pronounce it, you delete one I. So it is nil trium. Moving ahead. Very famous questions these are. Now, this is your name. 2020 question. You have to tell number. What is un 1? What is nil 0? What is n 9? And suffix it with em. So 109, option D. Piece of cake. Moving ahead, if IUPAC name of element is this and it belongs to nth group. So first, let us find the name. Em. As in the atomic number is 111. Now you have to tell the group and write the group number as an integer type answer. Sir, till 103, we know it is actinoid will end. So after 103, 104 will be there are D block. How many elements are there in D block? 10. So first is actinium, it is 89. Second one is 104. You tell me what will be the last one? Sir, 89 plus, okay, those are gone. So 103 plus 9 is, 103 plus 9 is 112. So D block, last element will be 112. What will be its group number? Sir, S block, 2 groups gone. So 2 plus 10, so this will be 12th group. So obviously 111 will be 11th group. So 11 will be your answer. So this is how you should remember the periodic table which we have discussed till now. So let us now quickly jump into the filling of Mendeleev's periodic table, which we said that we'll be doing after modern periodic table, because modern periodic table that we have learnt, it will be revised and the corresponding group and period relating to Mendeleev's periodic table will also be easily accounted by us. Now, what are the first group? Sir, alkali metals. So, alkali metals will occupy first period, first group, hai, li, na, ki, rab, se, paryad. So, as per these 7 periods and the first group. Remember, one thing you should remember about Mendeleev's periodic table, that in the sub-columns, A side of each column will be occupied by the representative elements, and the B side is Mendeleev has segregated, has designated for the transition elements. That you should keep in mind. A side is for representative elements and B side is for transition elements. Okay, sir. We did the first group. Now, what about the second group? We'll start from beryllium. So, beta, mange, potassium gets car, calcium, then strontium, beta, mange, car, scooter, barium, bap, razi, as in radium. So these are also filled: beta, mange, car, scooter, bap, razi. So if somebody asks you What is the position of radium in Mendeleev's periodic table? So it is 2a column and 10th period. Now, moving ahead, sir, after calcium, we know calcium is I told you, after modern periodic table, it is much easier for everybody to fill. So, after calcium, what we have in the second group, in the next group, scandium. So calcium, scandium, but scandium is a transition element, a D block element, so we'll be occupying the B subgroup of the next column. So this will be scandium, as in 3B is scandium. Now, next group but B column. So Shak, what was our rhyme from 21? Shakti Wo Kar Man. Now, 8th will have all transition elements. Man, Pe, Ko, Ni, and after Ni, Sujan. But where copper will go? In the next period. So, Sujan. So, it is copper. I'm sorry. So, copper will be first group, but over here. So, this is Su and this is Jan, because I need groups beneath copper also. Why? Because remember, zinc, cadmium, mercury, leaving one gap. We are writing these elements because then it will be belonging to the. So what will be the place of cadmium? 7th period and 2b group. Now, remember one thing also, the first column, the demerits of Mendeleev periodic table. First group has A and B. A has alkali metals, while B, remember that point, B had coinage metals. Both are present in same group, but properties are different. Copper, after copper, what we have is, copper, silver, and gold. This is how you fill Mendeleev's periodic table as well. Okay, sir. Now, what about, move after beryllium, what we have? Sir, third column A, because it's a representative element. So, third column A side will be covered by boron, because after beryllium, I have boron. Post boron, I have carbon. Post carbon, I have nitrogen, then oxygen, then fluorine. After fluorine, what about inert gases? A separate group. So let us write inert gases. Na, argar, kar, zero, run pe. See, this is how, because now we know modern periodic table, so we are filling Mendeleev's also. With this, just one thing in mind, that A is represented by representative and B are for transition elements. Now, you have to fill, I mean, 1-2 times you have to make by your pen, then only you will remember it for longer period of time. So, sir, what about boron family? You can very well draw the boron family. Baigan, aloo. Now, what about gajar? Gajar will come after zinc. So, not in the 4th period, it will be in the 5th period. So, baigan, aloo, gajar in Hela as in thallium. What about carbon family? Ka, Shi, Gaye, Shankar, Parvati. Next is nitrogen family. New Zealand, Pakistan, Australia, Sub, Bikau. The symmetry we picked from Baigan, Aloo, Gajar. This gallium will be coming after zinc as per the mass. So after zinc, if it is its position, then we are synchronizing all the corresponding groups then. Oxygen family, us, se, tipo. Then halogens, fluorine, chlorine, bromine, iodine, astatine, because halogens are so famous that I do not wish you also to learn within any rhyme. Now, these all things are done. Now, this is scandium is 3D series. Next is beneath is 5D series starting from yttrium. So just beneath this, because it was gallium and it is diagonally up. So indium, it will be diagonally up. The symmetry we know also, leave one gap and write the elements. So Yari, Zarasi, because B section. Nibha, Yari, Zarasi, Nibha, molybdenum, moth, tak, then go on. रुकावट, राह में पड़ी है PD, nickel, PD, PT, remember? So putting it like that, PT, Again, I have reached the next period after yttrium. So it is for lanthanides. So this is La, Haf, Ta, Varna, Re, Usdhar, Irdhar, Pitunga. So this is how beautifully we now, for example, how a question, because this periodic table is given in NCERT. So how question can come? Can you tell the place of, let's say, selenium in Mendeleev's periodic table? Yes, it is 6A and 5th period. So this is how this periodic table, because given in NCERT, this is also going to help you a lot. Moving ahead. Yes. So moving forward, let us characterize some important characteristic of these 4 blocks that we just read. So coming to S block, we very well know NS1 is the general electronic configuration for alkali metals, while NS2 is for alkaline earth metals. Mind you, hydrogen is not considered as an alkali metal. Similarly, beryllium is also not considered as an alkaline earth metal. So hydrogen is a group 1 but not alkali. Beryllium is group 2 element but not alkaline. Why hydrogen? Because definitely hydrogen is not a metal, it's a gas, while all other alkali metals are highly reactive solid metals. Highly reactive metals. Speaking of hydrogen, its oxidation state may be -1, maybe +1, while all alkali metal shows an oxidation state of only +1 in their compounds. Now, coming to alkaline earth metals, their oxidation state are always +2 in their compounds. Beryllium also exists in +2 oxidation state, but the reason why beryllium is not considered as an alkaline earth metal, because all alkaline earth metals are generally exist in nature in earth crust in form of their oxides, and all of their oxides have a basic nature, because we very well know metal have a tendency to give electrons. So whatever oxide metal forms are generally electron giving, so they are basic in nature. But beryllium oxide on the other hand is amphoteric, and hence it is not considered as an alkaline earth metal because it is not alkaline. It reacts with acid also, it reacts with base also. A very famous reaction: with acid it forms a salt, neutral salt, but with base like NaOH it forms berylate, as in a complex with barium having 4 hydroxyl group. So now coming to the radioactive nature, these alkali metals and alkaline metals we study till ली ना की रब से फरियाद. Fariad as in francium we do not study, and radium we do not study, because generally we are scared of radioactive substances. They are meant to release so much of energy that radioactive substance we generally do not deal, and JEE also does not like so much questions around them. Moving ahead. Sir, like I said, all alkali metals, they are not solid at room temperature. Cesium and francium, they are liquid metals. If you place cesium in your hand, it will turn liquid, although you can take out from a freezer, it will be a solid. Once it goes to your hand, it melts. So it's a liquid at room temperature. Alkali metals, as we all know, they are very reactive. So they are so much reactive that they even react with moisture. That's why they are kept in inert solvent, like sodium and potassium are kept in kerosene, whereas lithium, being as we go down the group, reactivity increases because atomic size increases. We'll be discussing it. So lithium can be kept in a wax. Moving forward, going to the P block elements, as we already know, the Mendeleev periodic table that we just did. Boron family is 3A and 13th group of our modern periodic table, while halogens are 7A, while 17th group. So these 6 P block elements we know, and mind you, helium. Helium electronic configuration is 1s2. Its last electron is going in S subshell, but still not kept in S block. Why? Because its properties analogous to these inert gases and hence kept here. Now, but it is not a P block element, but kept there because its property corresponds to the halogen, the inert gases, the noble gases. Now, some important characteristic of p block elements, obviously the electronic configuration ns2 np 1 to 6. These will be np1, they will be np6, and obviously snp has the same number as the period number in form of their principal quantum number. Now, generally p block elements are non-metals. Generally non-metals are gases, generally. So who are gases at room temperature? Nitrogen, oxygen, fluorine, chlorine, and all the noble gases. They are, even group 18 are also called noble gases. Sir, some are liquid also. Yes, you can find bromine and gallium in liquid state at room temperature. So there are some radioactive, obviously. Down the group, you always find radioactive substances. So after bismuth, after Bi, after bismuth, all are radioactive in nature. Now, do we find metalloids also? What is a metalloid? Having property of metal also and non-metal also. As we go down the group, metallic nature increases. So beneath you find metals, upside you found non-metals, but metalloid, a very important point. Metalloid, germanium, arsenic, antimony, selenium, and tellurium. These 5 are p block elements, but are metalloids, not metal, not non-metal. They have a property of metal also and non-metal also, hence called metalloids. Which is the best among them? Which is the best conductor but a non-metal and a conductor? Obviously carbon in form of graphite, not diamond. Now, this you can leave also, but for ABCD purpose, I guess you should know. Obviously, we know group 17 is halogens. We very well know this. Now, the new thing that I'm going to tell you is group 13 is called icosagens. Icosagens is a Greek name that are given to them because of their position in the previous periodic tables. Group 14 are also called crystallogens because they generally form crystals, solids. Group 15 are also called nictogens. Nicto. They are choking in nature, hence derived the name. Group 16 are also known as chalcogens. This is also there in NCERT. Why chalcogens? Because they are ore producing elements. Most of the metal that their ore that are present in nature are present in their form, oxides, sulfides, therefore chalcogens. Halogens, we know. What are aerogens? Derived from the name that they are freely found in air, gaseous state. So aerogens are also a name given to noble gases, group 18. Moving forward, some important characteristic of D block. As we know, we have 10 groups. So this 10 vertical columns are D block. General electronic configuration we have already seen. NS 0 to 2, as I've told you, we'll see in D block also. Like copper, chromium, 1 electron goes. Actually, in case of nickel, platinum, palladium, not nickel, but over there, 2 electron also goes in the inner penultimate D subshell. So general electronic configuration becomes NS 0 to 2 and N minus 1, obviously D 1 to 10. Who are volatile? As I've already told you, zinc, cadmium, mercury. They are volatile, as in they easily converts their solid state into gaseous state. Coinage metals used as coins, copper, silver, gold, we very well know. Sikka, in the kingdom time of ancient world, they were used as coins to make coins. Noble gases, noble metals, among these are metals, but there are among them these 4 metals are, they react, but they rarely react. I mean, with extreme conditions. Who are they? Mercury, silver, gold, and platinum. Now, obviously we know mercury is a metal which is found in liquid state and room temperature. First man-made metal. Man also made metal, that is TC, technetium. Now, best metallic conductor? No, it is not copper. Copper is cheaper. Actually, best metallic conductor is silver. Maximum oxidation state shown by D block is for osmium and Ru, ruthium, that is +8 oxidation state they show. What is delta HA? Thermodynamics, our previous chapter, like a solid changing into gas, also termed as enthalpy of atomization. So who has maximum? Vanadium, V. And who has minimum? The volatile one, zinc. Although zinc, cadmium, mercury, as the group, as we move down the group, mass increases, so relatively their enthalpy of atomization is higher, but zinc has the least enthalpy of atomization among D block elements. Moving forward, finishing it fastly, going to F block elements, sir, NS2 will be filled. Then n-1 d, again 0 to 1, because sometimes electron can go to inner shell to make 4f14. So that we'll see in electronic configuration. That's why this 0 to 1, and obviously n-2f 1 to 14. Obviously, these F block elements, they are rarely found in nature, so they are also termed as rare earth metals. Common oxidation state, actually lanthanide gives just same reaction as aluminium. Remember our redox chapter, aluminium always forms compound in +3 oxidation state, and so do lanthanoids, although they show other oxidation states also, but the most stable oxidation state for all lanthanoids are +3. Actinoids, they are generally radioactive, not studied much, but still, if you grab neck, what oxidation state they exist in, +3 and +4. Only synthetic, or lanthanoids are generally not radioactive. The only synthetic lanthanoid is PM, promethium, the only radioactive lanthanoid, whereas all actinoids are highly radioactive in nature. But the first three actinoids, थोड़े पहलवान उनसे, thorium, Pa is protactinium and uranium. These first three, although they are radioactive, but they are naturally occurring in nature. Most poisonous is plutonium, Pu. In fact, plutonium is also, because of its poisonous nature, it is also used in atomic reactor and atomic bomb. So plutonium is used. Now, sir, but we have read uranium. Uranium is actually used as nuclear fuel, and also in medicinal industry and glass and textile industry, uranium has found its application. These are all chemistry and everyday life questions. So just have a look over them. Now, used as fuel rods and in cancer treatment, TH, thorium. Maximum oxidation state, but as I've told you, they are radioactive. They must be reacting vigorously, violently. So the maximum stable oxidation state is shown by obviously uranium, which is +6. Maximum, if during such reactions you excite these elements a lot, they may attain a higher oxidation state, that is +7, but that is not stable, and attained by neptunium and obviously this radioactive species plutonium. So these are some basic facts I guess you should keep in mind, and moving ahead. So before moving to periodicity, the main aim of learning periodic table, let us revise those concepts that we have learned through few questions, although not a PYQ, but still very important as per the summary of whatever we have learned till date. So this is an electronic configuration and you have to tell me to which block it. So we have done such type of question. I am summarizing. Krypton. So krypton is hai, na, agar, kar. Fourth period. Okay, sir. Fourth period as in till 4p6 krypton must be filled. Sir, we know. Sir, can't we see directly? No, because we know first what is filled, Ns, then n-1d if exist, then Np. So whenever an electronic configuration is given, you should always go by the basic which we have learnt till date. So krypton is, sir, fourth period, last element, so 4p6. So post krypton, because krypton is hai, na, argar, kar. So that is krypton is your fourth period element and even the last one. So sir, after 4p6, what will be filled? Fifth period. So it will be 5s2. 5s2 is there? Yes, sir. Then what comes? Sir, fifth period does not have D block. Okay. So what is filled? 4. So it does not have F block. So what is filled? 4d10. After that, 5p6. Just check. We have 4d10. Yes, we have 4d10. We have 5p6. Yes, we have 5p6. So that means it is filled till fifth period. So after that, sixth period. Sixth period, 6s2. Then what comes? Sir, that one lanthanum is filled first. So that is what? 5d1. And post that, sir, 4f is filled. So 4f14. So let us check 6s. Yes, 6s is there. 5d, sir, I cannot see 5d over here. But sir, I can see 4f. We can very well see 4f. Now, actually, I told you, na, I will be discussing these DNF block and DNF block elements also, but it's because you know through chromium and copper that we have done in atomic structure, and I've explained here also, that in case of chromium and copper, one electron from the valence shell comes to the inner penultimate shell. in order to provide stability of half-filled and fully filled electronic configuration, remember. Similarly, sir, in F also that can take place? Yes. So what are the examples? We'll do there. But by just going with that basic, can you tell me that, sir, maybe this 5D electron can migrate to 4F and make 5D 0 and 4F 14? That's why you are not having 5D 0 configuration, although it is a very precise case of that D and F block element, but the logic is coming from this periodic table and atomic structure logic only. So you tell me where the element will be filled, sir, in F block. So it must be an F block element. A beautiful question inculcating whatever logics we have learned till date. Moving ahead. Again, now this is an important question, but this is, I told you, Mendeleev's periodic table numbers are also important. Let us prove it. Now you are asked that you are given an electronic configuration. Sir, fourth period. Okay. So after 4s2, sir, but 3D will be filled. Oh, the question is not telling you, it must be filled. But if the question is not supplying you with that inner shell, what will you do? But it is telling you, no, that 4p is also filled. By how many electrons? 2 electrons. So it must be a p block element. That too what? Sir, 4p2. So 4p1 will be 13th group and 4p2 will be 14th group. So we know it is a 14th group element. And what will be the period number, sir? Principal quantum number n. So period number we very well know 4. Period number we very well know 4. So we are landed with option B and option C. But sir, remember in Mendeleev's periodic table, groups are represented in Roman numerals. So you just go and check in our periodic table. Let me do that for you. I mean, you can check in the periodic table also, but here. This is, okay, this is D block. What about P block? Ha, sir, it is 4A. So if you, that's why we made that Mendeleev's periodic table as well, because I told you that was also asked in your JEE question because the table is given in NCERT. So this is 4A. So answer is C. Moving ahead. All now a very important logic, again a D and F block element logic, but you should be originating from periodic table. So I am including everything. Now D block elements are those elements in which the last electron goes to the D subshell. Cleared, done the characteristic as well. But D block elements are also called transition elements. Like S and P block elements are called representative elements. I have repeated it many times, telling you again. D block elements are also referred as transition elements. But zinc, cadmium, mercury, these three, zinc, cadmium, mercury, these three, they are D block elements. They are D block elements, but they are not regarded as transition elements. Why? Because it is a theoretical definition. And the definition says transition elements obtain their property, their characteristic, because they have either in their ground state, as in their atomic state, or in any of their oxidation state in which they form compound in nature, they should at least have one d orbital that should be either empty or half filled. Then only that electron transaction may take place. So all D block elements are termed as transition elements? No. Only those D block elements are termed as transition elements who have at least, for example, you have copper. What is electronic configuration of copper, sir? We know it is 4s1 3d10, sir. D block is here also completely filled. So this should not also be a transition element. But we know that copper sometimes also exists as copper +2 ion. So when you are supposed to remove electron, because we are filling electron as per Aufbau rule, as per the electronic configuration rule of quantum theory. But sir, when you are taking out electron, which electron will be removed first? The outermost electron. So which electron will be removed first? This 4s electron will be gone. And after that, one of the 3d electron will also go. So it will become 3d, it will become 3d9. So at least copper in its +2 oxidation state has this d orbital, which is incompletely filled, and hence electron transaction can take place. So a d block element acquires a name of being a transition element only when it has ability to transact electrons with others, as in it must get involved in certain sort of chemical reactions involving d orbitals. But for that, d orbitals has to be empty. Their d orbital is never empty, neither in their ground state, and what oxidation state they acquire? +2. And in the +2 oxidation state, only their ns electron will be gone, their n-1d will always be filled. So this is a very famous question also, a theoretical reasoning also that you should know. Now, sir, the main side of periodic table, which is the learning of periodicity. What is periodicity? Gradual change in properties when we move down the group or along the period. Now, because we have discussed the periodic table very in detail, in depth, so let us go into directly jump into this periodicity, which I guess is very easy, just you have to remember these basics, what I am giving you. So, inorganic, it will be helping you like anything. Now, before starting the periodicity, let us learn the first topic. The first topic is screening and effective nuclear charge. Now, sir, we very well know nucleus is like a positive center. Electrons are revolving around nucleus. Atomic structure is that way only. Now, what is the atomic size, sir? Distance between nucleus and valence electron. We all know this, that is atomic size, distance between nucleus and valence electron. Okay. Now, why the electron is revolving in their respective orbit? Sir, because the attraction to the electron by nucleus and the centrifugal force must be getting balanced. But the attraction from the nucleus will definitely depend on the nucleus, the protons, the nuclear charge. So does that electron, that valence electron, feels the equal amount of attraction which the nucleus offers? No. The valence electron, actually the amount and level of attraction felt by the valence electron due to the nuclear charge is not entirely because of the nuclear charge. Why? Because this nucleus having this positive charge is definitely welcoming this electron. So there is this force of attraction, attracting, but it is getting repelled by not only because of centrifugal force, but it is also experiencing repulsion from the inner shell electrons. Like it is nth shell, the valence shell. The first inner shell is known as penultimate shell, the n-1th shell. Similarly, the n-2th shell will also have electrons, and we very well know electron repel each other. So actually, what this nucleus is effectively attracting to that electron is termed as effective nuclear charge. And this effective nuclear charge is termed as Z effective. And the Z effective is obviously depending upon the number of protons present, which is Z. But it is subtracted. It is subtracted by this factor of sigma, which is called the screening effect or shielding constant. It is statistically calculated by Slater, and therefore sometimes it is also called Slater's constant. So point is, it is very easy. If a teacher is teaching in a class, the teacher is the nucleus. The student, if you are, let's say if we are meeting in a live class and you are sitting in your benches, so the student sitting at the last is the valence shell student. So the number of electrons, number of students before that student will also be hampering the attraction force between nucleus and that valence electron. And the repulsion forces offered by the inner shell electron are called shielding constant or shielding effect. And effectively what that valence electron is feeling attraction, that is not my complete charge. My complete charge minus shielding. So this is the basic formula which you should, actually Slater's rule also tells us to calculate the value of sigma. But for mains, you do not have to learn that formula. Although I'm not even giving you formula, I'm just giving you the trend so that you may at least remember one thing. What one thing, sir? Point is, this value of Z effective, now I'm directly going to first I will be showing you this slide, but first I'm directly going into the summary of Z effective because I need periodicity. So what is Z effective again, sir? Z effective is the effective nuclear attraction felt by the valence electron, and it is equal to Z, which is number of protons, but this is subtracted by the shielding constant sigma, calculated by Slater's rule, but we are just going into the conclusion part of it. What is the conclusion? Periodicity is the gradual change. So when you move down the group, you will find that the value of I am talking, this periodicity I am making for Z effective. When we move down the group, we find the Z effective value remains constant. It does not change. Sir, but as we move down the group, nuclear charge increases, but because of repulsion offered by the inner shell electrons, effectively valence electron feels the same amount of attraction. Therefore, effective attraction remains constant. And when you move along the period, this is called moving down the group, this is called along the period. This is the whole soul of this chapter, this periodicity, the gradual change. And when you move along the period, obviously, Z effective increases. Now, you have seen periodic table. Like for example, here moving down the group, sir, first shell, second shell, third shell, fourth shell, fifth shell, number of shells are also increasing. So electron are going in the next shell. Effective nuclear charge is not at all increasing. So that's why down the group size increases, because according to Bohr theory, what we know, that radius of nth orbit is directly proportional to orbit square. For example, if radius of first orbit is a, then radius of second orbit is not 2a, it is 4a. Radius of third orbit is square times 9a. Fourth orbit is 16a. Why it is so? Because down the group, although nucleus is also getting proton, but it is not able to attract those valence electrons. Those valence electrons are feeling the same attraction, which is felt by the element that are having lesser protons. For example, lithium has in second period, lithium has how many protons in its nucleus? 3. The 3 protons also offer the same level of attraction to the second shell electron as the 11 protons of sodium. So sodium must be having 11 protons in its orbit. You keep that 11 proton. We have no profit of those 11 protons, because those 11 protons are not giving any amount of attraction to us. They are giving us the same amount of attraction which lithium electrons are experiencing. Moreover, the electron is filled in the next shell, so it is not at all feeling attraction. Therefore, down the group, why I am iterating it again and again is, down the group, Z effective remains constant, and because of this, directly going into the main periodicity, atomic size. Therefore, atomic size down the group, it doesn't increase, it increases to a large extent. Therefore, whenever you have to compare properties of anything down the group, you always first give preference to the atomic size that it is getting increased. Now, along the period, this Z effective keeps on increasing. So, electron is filling in the same shell, plus effective nuclear charge is also increasing. So, electron must be attracting the valence electron. So, if valence electron gets attracted, its distance from the nucleus gets reduced, and therefore along the period atomic size decreases. However, this decrease is small in magnitude, while this increase of size is much larger in magnitude. So this you should keep in mind. But now I am giving you this. Again I'm telling you, you do not have to learn the Slater's rule to calculate. Just go to this basic. This is also very easy. There's a fact, some electrons contribute 0.35, some contribute 0.85, some contribute 1. So these are some set of rules, not at all required for mains. Moving here. You just check that I have given an example of these elements are along the period. They are along the period. So these second period elements, you just check. The second period element, the effective nuclear charge is getting increased. So along the period, effective nuclear charge is getting increased. Electron is filled in the same shell. also experiencing more attraction, so size will get reduced. So atomic size reduces. Now, down the group, I told you, down the group, if you apply Slater's rule, Z effective remains constant. See, from lithium to sodium, although there is some increase, after that, the value is almost constant. And therefore, nucleus is not at all, although it is getting very strong, but its strength has no contribution to the valence electron. So valence electron will keep going dur, far, is my point. So down the group, atomic Z effective remains constant, therefore atomic size increases drastically. Now one thing. This is an add-on, by the way. No? We'll be doing this then in D block and F block also. Now, in general, when we go to D block elements, what is observed, I mean, we do not have to calculate. I'm just giving you this example to observe. What observation, sir? Along the period, what we said, Z effective goes on increasing. But here, the increase is quite small. If you check along the period, the increase is quite large by a factor of around 0.85. By a large factor, you just leave the number. When for a normal period, for a normal S and P block element along the period series, so along the period, Z effective increases by a large extent. But for D block elements, you just watch this, although it is getting increased. Therefore, along the D block element also, if you go along the period, their size increases, their size decreases, because Z effective is increasing. But this increase is not that much in magnitude. Moreover, when you go to the last, almost the end side of 3D and any D block element series, the effective nuclear charge starts decreasing. Therefore, we will see there also that in D and F block elements also, that along the period atomic size decreases. But this decrease is quite small for D block elements. And in fact, for zinc and copper, the atomic size increases. Why increases? Because Z effective decreases. What is Z effective? Effectively, how much nucleus is attracting those valence electrons. So this is a beautiful example, a technical detail of how you see the Z effective and atomic size properties. Now, moving ahead. Sir, atomic size periodicity you have told. Then why again atomic size? Atomic size you know from class 9. Distance of nucleus from valence electron. Quantum theory you also know. Can you put out a inch tape or a scale, put that scale in the nucleus and measure this electron? Is it a Dahmer road where you can put this scale and measure this distance? No. Through spectroscopy also, can you ask this electron to stop so that you can measure this length? No. Moreover, atoms in nature are not at all found in atomic state. Very rarely, only inert gases and few elements exist as atoms. Rest everybody exists as molecule. So point is, atomic size, what we have defined is definitely correct. The periodicity which we have seen is definitely correct. How will you measure the atomic size? So in order to measure the atomic size, certain definitions of atomic size was defined. So you first have to know those definitions, because atom does not exist in atomic state. And if at all, if it is existing also, it is practically, experimentally impossible to calculate distance of nucleus and valence electron, because this electron through atomic structure, we know they do not have a property of a mass. They are wave. So how will you put a scale and measure a distance between a mass and a wave? Because it's an energy. So point is, in order to calculate, in order to estimate the atomic size, some definitions have to be given by scientists, that how is it possible? What are the approximation that we are making to calculate the atomic size, to experimentally detect the atomic size of elements? So therefore, some definitions of atomic size are given, which are 4 in number: covalent radius, ionic radius, metallic radius, and van der Waals radius. Ionic radius I'll be discussing separately. First, I'm discussing these 3: covalent, metallic, and van der Waals. We very well know elements, covalent radius, we very well know elements in nature, mostly they exist as covalent, mostly as in P block elements, mostly they exist as covalent molecule. What is a covalent molecule, sir? Formed by sharing of electrons. Okay. So let's say there are two nucleus A and A forming a bond. Okay. Now, how can you draw their picture, sir? There must be sharing of electron taking place, hence the circles are overlapping. We cannot measure those electrons because they are wave, but nucleus is quite heavy. So can you find the distance between this nucleus and this nucleus? Yes, sir. Experimentally, spectroscopy through by throwing laser, it can easily be experimentally detected. So the distance between two covalently bonded atoms can be detected. Let us say this distance is d. This distance is d. So what scientists theoretically assumed was they divided this d by 2. So half of the distance between two nuclei was theoretically given the name as covalent radius. But sir, this is not the exact radius. This is the only way you can find atomic radius. But whenever this radius is defined, they also serves you with the knowledge that this is their covalent radius. Sometimes they do not, but you have to understand that because, for example, it's hydrogen. So hydrogen in nature exists as what? H2 molecule. So for hydrogen, if atomic radius is given, then you have to know also that what will be that radius? Covalent radius. So this is a covalent radius, that is half of the distance between a two covalently bonded atom, because these nucleuses distance can easily be measured. Now one more thing, sir, if these two elements are electronegative, let's say this is A, this is B. What is electronegativity? Just basic thing. If I have more protons, the shared pair of electron I will attract towards myself. So let's say B is more electronegative, so B will attract these shared pair of electrons. So it will attain a partial negative charge and it will attain a partial positive charge. What ionic compound do? They completely take one electron. So a species taking complete electron becomes negatively charged minus. The species losing electrons become positively charged cation. Attraction between them becomes an ionic bond, ionic attraction. But here I am talking covalent bond. But covalent bond can also be formed between two atoms of different electronegativities. So they may not be very electronegative. If they would have been very electronegative, they would have formed ionic compound. They would have completely taken electron, became a minus, and that who has lost become the plus. But when they are covalent molecule, like for HCl, hydrogen and chlorine. Chlorine is more electronegative, so it will attract electron towards itself. Which electron? These share pair of electrons, and attain a partial negative charge, and it attains a partial positive charge. So HCl will be a covalent molecule, but what type of covalent molecule? A polar covalent molecule. Similarly, H and H will be a non-polar covalent molecule. Very simple things which you should know. That because of electronegativity difference, if I'm attracting that shared pair of electron, that person will definitely come closer to me. So point is, as electronegativity increases, atomic size decreases. Two atoms approach close to each other. This also you should know. Now, this although for mains this definition I have given for those 1, 2, 3 students who must be feeling, no sir, we want more. So I have given that thing also, that normally it is the distance by 2. But if it is heteroatomic molecule, the distance can be taken as Ra plus Rb, but subtracted because of electronegativity difference, the distance will get reduced. Mind you, formula not required, although I have written now. But there are some more formulas given by Pauly, not at all required. They are just given by, I mean, in advance they may, practically telling you, advance also do not. They just ask whatever logic is there in NCERT. Moving ahead. Sometimes they ask. That's why people teach also. Now, moving ahead. Sir, covalents. Do all atom exist in form of covalent molecule? No, sir. Like for example, you have metals, sodium, potassium. Those metals, they exist as solid metal. So what is the basic idea of a solid for you? So solid as in constituent are closely packed with each other, but the overlap will not be picturized, because overlap was picturized when covalent bond was getting formed, because in that case actually electron overlapping take place. But if you are a metal, I will just think of you as a solid species. So one constituent, another constituent, and a solid can, what is the maximum distance a solid can approach each other? Electron, we are not considering covalent. Okay. So still nucleus will exist? Yes. Still distance between nucleus you can experimentally observe? Yes. Divide that distance by 2, you will get half of the distance. And this half distance will be termed as metallic radius. Like for sodium it is calculated. And it is giving you an example also that for potassium, I am giving an experimental value also. For potassium, metallic radius is found to be 2.3 angstrom. But you can find covalent radius also experimentally, which is 2.03. Sodium making some covalent bonds. In that case, if its radius is calculated, then it will be a covalent radius. So through this picture also, you can see when covalent bond is formed, nucleus will be slightly closer to each other because electron transaction are taking place. So they'll be closer to each other. But once you are calculating the metallic bond, the distance d is large. So half of distance will also be large. So the point is metallic radius is greater than covalent radius. But for a similar species, metallic radius of somebody, covalent radius of somebody will not be compared. For a similar species, its metallic radius, if measured, is definitely greater than the covalent radius. And one last radius, van der Waals radius. What is it, sir? Like for example, we know helium. So it's a monatomic gas. So helium must be existing like a gas. No covalent bond, no any bond. How will you calculate atomic size of inert gases? Helium. Difficult. So, but distance between nucleus can be measured. So you do one thing. You take those molecules. So those molecules are atomic species only. So that is a molecule. So helium molecule is helium atom. So let's say this is helium atom. One helium atom must be attracted by another helium atom. This is told in states of matter because it is out of JEE syllabus. So I'm telling you, the physical force of attraction between any constituent is defined by van der Waals, and forces are called van der Waals forces of attraction. These van der Waals forces of attraction are basically the attractive forces between two species. If that van der Waals force of attraction is large, the species are closer to each other, forms a solid, less liquid, very less gas. To this van der Waals forces of attraction, we will give some discussion time also in chemical bonding. But van der Waals forces of attraction are basically intermolecular forces of attraction. Now, every gaseous molecule also have some, although very limited amount, but they have some van der Waals force of attraction, some force of attraction. So these van der Waals force of attraction must be there. So one atom will be, although they may be far, but you can consider two. If this ball and this ball is this much far apart, but still the distance between adjacent atoms can be found. So experimentally it was found. Half of this distance is termed as the van der Waals radius. Sir, but this will be very large. Yes. So if you calculate van der Waals radius for any species, it will be much larger than the metallic radius. And what will be the most smaller one? Covalent radius. That's why in periodicity of atomic size, what we have seen, atomic size increases down the group and decreases along the period. But this decrement is only valid till 17th group, not for 18th group. Because for 18th group, what radius is determined? Van der Waals radius, which is definitely larger in magnitude. So when we say this periodicity, that periodicity atomic size decreases along the period. This decrement along the period is only valid till group 17. For group 18, it is not valid. The atomic size is not large. It is actually the largest in every corresponding period. If you calculate the atomic size of neon is not large. It is largest, it is even larger than sodium, because for every element, what radius has generally defined? Either covalent or metallic. But for inert gases, they are the only radius that can be found for inert gases are van der Waals radius, which are these. So while given molecules, like for example, it's a chlorine molecule, Cl bond Cl. It's also a chlorine molecule. So for chlorine, you can very well find the covalent radius. But sir, for chlorine, this distance can also be measured. Let's say this chlorine nucleus is this chlorine nucleus is. So distance between atoms, although of different molecules, but distance between adjacent atoms, half of this distance, half of this d can be calculated, can be called as van der Waals radius, which will definitely be greater in magnitude. But you should know what is the definition of van der Waals radius. Moving ahead. Now, this I have already told you that van der Waals radius is largest followed by metallic radius, and the smallest is covalent radius. But you should only compare this for similar species, not one species of that and others, generally for similar species. Now, so this all things, although I have given for chlorine, the value are also I have given. For chlorine, van der Waals radius is 1.8 and covalent radius is 0.99 C. Almost double, almost. Now, so moving ahead after this, so quickly moving forward, let us discuss the size of ions, the ionic radius. Distance of nucleus from valence electron in an atom is atomic radius. When this is an ion, the radius is ionic radius. Why discussing separately? Because in general, the question that JEE frames is regarding the isoelectronic species and their sizes and their ions. Let us compare with a neutral atom, neon. How many protons, electrons it has? 10, okay. What are isoelectronic species? Having same number of electrons. So Na plus, although have 11 electrons, if Na plus is formed, so 1 electron is gone, so 10 electrons. Mg plus 2, 10 electrons. Similarly, N3 minus, 10 electrons, because nitrogen has 7 electrons, but N3 minus will gain those extra 3 electrons. We very well know number of protons inside the nucleus remains the same even in the ion. And these electrons must be playing a tug of war game with the nucleus, because we very well can see the equilibrium distance between nucleus and electron is called the atomic radius, and for ions it will be called the ionic radius. Now, my point is, if outside number of electrons are same, so a game of tug of war that is happening, like in this case, there are 10 electrons outside. Okay, not all 10 electrons are outside, but electronic configuration will be such that because number of electrons are same, so number of all valence electrons will also be same. So my point is, number of people pulling the rope from outside as equal. So who will decide the size? Number of protons inside. So the species which have no more number of protons will pull these electrons and size will reduce. Where the number of protons are more? Sir, in the cations. While in the anions, the number of protons are minimum. So if proton is minimum, they will be applying the attraction force to a minimum extent and size will increase. So my point is, anions are larger in size while cations are smaller in size as compared to their neutral parent species. So this is a very common sense which you should always remember, highly asked by JEE. So for example over here, which will have the highest size? N3 minus, followed by O2 minus, followed by F minus, then neon, then Na plus, then Mg plus 2, and who will be minimum? Sir, Al plus 3, because obviously it will also be isoelectronic. Sir, was asked, yes, JEE question. I mean, a lot of questions are such as, but how beautifully JEE has asked this question. They have given you N3 minus, O2 minus, F minus. Sir, more be the negative charge, more will be an ion size. This is for isoelectronic species. So obviously, they are isoelectronic because number of protons in nitrogen is 7, oxygen it is 8, it is 9. Number of electrons 7, if it was neutral, because minus 3, so 10, 10, 10. So isoelectronic species. Who are pulling inside? Sir, 9 protons will pull more, so size will be reduced. So who will be of the largest size? Anionic size, sir, N3 minus. Now question has not asked you the order. Question has randomly given you value. So N3 minus should have the highest value. Which is highest? 1.71 is highest. So 1.71, 1.71, 1.71. This is wrong. Because 1.71 is highest and N3 minus should be highest. Then after that, O2 minus. So second highest will be O2 minus. This is 1.6, 1.4 is our list. This is okay. So this is also okay. So your answer is C. Now, how beautifully JEE has asked this question. The common sense has came many number of times. Moving ahead. So sir, atomic size we finally did, along with the knowledge of effective nuclear charge. Now, we will be discussing more of this atomic size relationship in D and F block elements, but because for S and P I'm summing it up, D and F will be doing separately. Now, certain facts will always be there. Now, what we'll be discussing next is, let us summarize what are the factors on which atomic size depends, because all other property we will now be relating with atomic size. So, what are the factors on which atomic size increase, sir? First, effective nuclear charge, that is Z effective, how much nucleus is attracting those valence electrons. If nucleus is attracting to a larger extent, obviously the size will decrease. So more be the nuclear charge, lesser be the atomic size. That's why Z effective remains along the period, Z effective increases, so atomic size decreases. Down the group, it almost remains the same, therefore atomic size increases, so they are inversely proportional. Now, number of shells, sir. As number of shells increases, distance between valence electron, through Bohr theory also we know, distance between nucleus and valence electron increases drastically. Because down the group, size increases drastically. Now, Sadik sigma, you said Slater's rule not required for JEE mains. Yes. Actually, in advance also, with the common sense that I have given you, that Z effective increases and down the group remains constant, and for D block element it increases but to a very small extent, and at the last, in case of copper and zinc, it increases. Now, sir, but should we know something else? Yes. One more thing that you will be needing is, if you go to the common sense that we have done in atomic structure, what is the shape of S subshell? S orbital, sir, spherical, very symmetrical shaped. What is shape of p orbital, sir? Dumbbell. I mean, that dumbbell is quite thinner. S orbital is quite fatty. So my point is, if I'm your teacher and you will be the valence electron, you will be the student sitting at the back. If there is another student between the two of us, and if the student is quite heavy, sir, if it is heavy, then I will see your face like this. You will also see my face like, sir. So more be the symmetrical shaped inner shell electron, more will be the shielding between nucleus and valence electron. Sir, easy. So who provides greatest shielding? S. Lesser than that, P. And the theoretical knowledge that you should keep is, D and F does not have less shielding. They are very poor shielding orbitals. F though is a gone case. D also provides poor shielding. F though is a gone case. D also is a gone case as compared to S and P. S provides here tremendous shielding. P provides less, but D and F has very poor shielding. Sir, this is used? Yes. Now, what we have seen? Down the group, atomic size increases. Remember? Now, there is a very notorious group that is group 13, boron family. Now, you do not have to learn the data. I just want to give you the periodicity. Why we are studying periodic table? Because we do not want to read all the data. But trend we should know. Periodicity we should know. What can you say about atomic size down the group? Sir, we already did it. Atomic size down the group increases. We know this. So what are we expecting? Size should increase. Let us see. First, let us check. See, for ionic radius, trend is always the same. Like just 27, 53, 62, 80, 88. Increasing, you just leave the value. Is the size increasing? Yes. So whatever trend atomic size follows, ionic size also follows. But in atomic sizes, sometimes some people say exceptions, I say they are logics. So what logics? And NCERT and JEE also loves those logic. What is that? So actually, if you I'm not asking you to learn and write these values, just know the trend. From boron to aluminium, 85 to 143, increasing. Yes, we are happy. It should increase because it is following periodicity. From boron to gallium, oh, sir, it is 143, this is 145. We are sad because this is against periodicity. 135 to 167, yes, sir, again increasing, so no problem. 167 to 170, again increasing, no problem. Now, point is, atomic size over here is down the group is increasing, but sir, I am not comfortable with gallium. What should I do? Go to your basic. What basic? The fact, shielding. How, sir? See, What we said, along the period, Z effective increases and down the group, it remains the same. Why it remains the same? Because inner shell electrons provide so much of shielding that the increased protons attraction is not at all experienced by the valence electron. Now, what I'm saying is, why group 13 is most notorious, because just before group 13, what start happening is filling of d orbitals take place. And you tell me from which period filling of d orbital starts? From fourth period. Fourth period is 3D series. So fourth period is just before gallium. Extra from boron to aluminium, there was existence of no d subshell. But from aluminium to gallium, filling of 10 extra d elements took place. So from aluminium to gallium, what increased by a factor of 10? Sir, Z increased by a factor of 10. Why? Because from boron to aluminium, whatever protons are getting added, after aluminium till boron, till gallium, 10 extra protons are added because 10 elements are filled. So proton extra 10 added in gallium. From aluminium to gallium, 10 extra protons are added. Z will increase. If Z increases, who will increase? Sir, if Z will increase, then Z effective will increase. Sir, but Z effective is not Z, it is Z minus sigma. So what I am saying is, what is sigma? Sir, shielding. Shielding of electrons are filled where? Sir, electrons are filled in 3D. Electrons are filled in 3D. What is their valence shell? For gallium, which shell is filled? 4p. So 3D is inner shell, and that too D and F they do not have less shielding, they have poor shielding. So the shielding offered by D and F electrons are not less, it is poor. So what I am saying is, this sigma is much lower. For whom? This sigma is much lower for D subshell electrons. So you just go by basic. Sir, if Z increases, mathematically Z effective increases. And sir, if sigma decreases, Z effective is increased to a much larger extent. And because of effective increase of nuclear charge, I will attract electron. And if I will attract electron, they will not be able to go out, as in far from me, to more extent. But sir, still for aluminium, the valence electron are third shell. For aluminium, the valence shell is 3s2 3p1, and for gallium it is 4s2 4p1. No matter you are an electron belonging to fourth shell, but my nuclear charge is increased to such a large extent that I have pulled you inside. How much inside? That your distance from me is 135 picometer, while for aluminium it is 143. That's why, because of this factor, which is atomic size is also depending upon the shielding effect, is a very beautiful, this example is a very beautiful example for explaining that factor. So ultimately, what is the trend? Down the group, atomic size increases, but there is an anomaly between boron and between aluminium and gallium. So how will you write the trend? So how will you write the trend? You will write boron, after that gallium, because what rhyme you know? Baigan, aloo, gajar, in thela. So this is a very famous example, that is order of atomic size of group 13 element. And why, how it is explained? This is explained via knowledge of shielding constant. Yes. So moving into the question says you have to tell the smallest radius among them. We obviously can see these are all ions, and for ions also periodicity is followed, that is down the group atomic size and ionic size both increases. So fluorine, chlorine, bromine, iodine. the atomic size also increases and therefore the ionic size will also increase. So smallest will be fluoride ion. So, but there is hydride ion also. Now this is a factual, now the almost the less loved thing about chemistry, but also the less loved thing sometimes, if you remember during the question, will save you and fetch you good amount of time also. Now what I'm trying to explain over here is hydride ion is larger in size. It is even larger than bromide ion. It is just smaller than the iodide ion. This is a factual thing that you should know. Some people give and advise to take out the ratio of electrons upon proton, E by P ratio. But that logic will also not help. So why learn a trick if that trick is not applicable anywhere? That's why I haven't given any E by P ratio to you. The thing that we know is cations for isoelectronic species, cations are always smaller for any species. If I'm the parent, my cation will be smaller than me, my anion will be larger than me. And for isoelectronic species, more be the minus, more is the size, more be the plus, less is the size. This is what we have summarized till date. And this is about this hydride ion, because hydrogen has a very small nucleus, only one proton. So its proton is not at all capable that if one extra electron is added, the hydride ion size increases such drastically that it is even bigger than the bromide ion. A factual knowledge for you. Moving to this other question of this is JEE Mains 2024 question. Now you'll see how beautifully and simply they ask. For isoelectronic species F minus, neon and sodium, you have to, it is affected by what? Sir, we were playing tug of war. Who was responsible for playing tug of war in the center? Sir, nucleus. So who will be deciding everything? Sir, nucleus and those number of electrons. Principal quantum number? No. None of the factors. Let us just read all the factors. Achha, he's saying because size is same. Rho, size is not same. Electron-electron interaction? No, sir. Electrons, if added, they take outside. So, electron-electron interaction, we are not at all considering. Nuclear charge. The more is the number of protons, the more is the nuclear charge, the lesser is the size for isoelectronic species. This we have already seen, just a theoretical question based on that. A direct question came in mains. Moving ahead. Again, an assertion reason. The assertion says there is a considerable increase in covalent radius from nitrogen to phosphorus. Sir, Group 15, nitrogen family, New Zealand, Pakistan, Australia, sub bikau. From New Zealand to Pakistan, nitrogen to phosphorus size increases, yes. Reason, however, from arsenic till bismuth, only a small increase in covalent radius. Now, as promised, I told you, this is a P block concept, but related with periodicity. I'll first explain, although we know the explanation, but I'm just relating with this case. Sir, atomic size increases down the group. Atomic size increases down the group. Look at the value. Increasing. We are happy. But sir, 56 to 98 almost doubled. 98 to 114 almost 15% rise. 114 to 133 increasing but very less. 133, 134 increasing, but the periodicity is not failing. Atomic size is increasing. Definitely periodicity of atomic size is perfectly correct. Not like boron family, because in boron family, like we have done, 13th group is just coming after the D block. Because just coming after, so 13th group shows, because of the filling of extra D electrons and D protons, the Z effective change creates a lot of difference in the properties of 13th group. Post that, the difference is nullified. See, over there, aluminum and gallium were getting interchanged. Here it is not getting interchanged, but the principle is just the same. What is the principle? Sir, arsenic is the fourth period element, because that is before arsenic, that 3D filling must have been taken place. So Z effective must have been increased as discussed before. Sir, if Z effective is decreased in case of arsenic, nucleus is quite strong. Sir, if nucleus is quite strong, it will not allow the size to be increased. I mean, periodicity is not getting changed as in case of boron family. But this impact the size increment is now reduced. So why size increment? Normally size increases drastically. But now, after arsenic, why the size is not getting increased? Because the introduction of poor shielding of d electrons, because of which Z effective is strongly increased. But with the same, because of the same reason, what is the effect? Effect is not that size is decreased. Size is following the periodic trend, but the increment has been reduced. So a same reason can create the difference in U. That difference may not be visible to the society. What is the difference? Size is still increasing, but the increment has been reduced. So what should be the reason? The poor shielding of F electrons. But what the reason this question is telling you? Covalent ionic radii in a particular oxidation state increases down the group. This oxidation state and increase of size or oxidation state will be depending upon the inert pair effect. So this has nothing, this is talking nothing about that shielding effect. So reason is obviously not proper for assertion, but covalent ionic radii in a particular oxidation state increases down the group. Yes, covalent and ionic radii in a particular oxidation state, like for example, for the ions, the question that we did before, halogens, atomic size increases down the group. Sir, what is the oxidation state that question was talking about? -1. So size of -1 was also increasing down the group. So size of a particular oxidation state, that is -1 in case of halogens, and for nitrogen family, the general oxidation state is +3, +1. That particular oxidation state, size of ions will also be getting increased. So the question is saying covalent ionic radii in a particular oxidation state increases down the group. This is also right, but not explanation of the assertion. So what will be our answer? Assertion and reason both are true, but not explanation, because the explanation is that poor shielding of D and F electrons. Nice question, a theoretical, a challenging question, asking you that whether you know the theory or not. Moving ahead. Now, the set of, again, this was an IEEE, JEE mains initially used to be termed as IEEE. The set which correctly represent the ionic radii. Okay, sir. Now we have to, compare the ions. Okay, sir. So let us draw them in a periodic table. Lithium, beryllium. Then beneath lithium I have sodium, and over here I have magnesium. Now, sir, we very well know what trend atom follows, their ions will also follow the same trend. What about the atomic size? Sir, atomic size increases down the group and decreases along the period. So obviously, lithium and among lithium, beryllium will be small. Among sodium and magnesium will be small. Now, how to compare these? Sir, ions, remember that. Ions, always you give preference to the charge, the oxidation state. They will form ion in which oxidation state? +2. So Be +2 and Mg +2 will definitely be decreased because size decreases. But sir, Be is less than Li, Mg is less than Na. How can you compare these two? That's what I'm telling you. That when a cation, when cations and anions are formed, you always first give preference to the charge. What is the charge we are talking over here? +2. More be the positive charge, lesser is your size. So I am giving first preference to the charge. That is, both the +2 ions are smaller. Both the +2 ions must be smaller. Yes, this can be an answer. Both the +2 ions will be smaller. So B will definitely not be an answer because it is saying it is larger. Both the +2, sir, both the +2. So this is also not right for us. Both the +2, yes. Now, comparing among Be +2 and Mg +2, sir, size increases down the group. So beryllium is smaller. So which will be the smallest? Sir, beryllium +2 will be smallest, Mg +2 will be, but option D is also giving you the same trend. So let us compare the +1 ions now. So +2 ions will be smaller, +1 ions will be larger. Now, larger than +2. Now comparing the +1, so again atomic size increases down the group. So lithium will be smaller and sodium will be larger. Na+ will be larger. So Na+ will be larger. Okay. The sign. It should be the smallest, then Mg plus 2, then Li plus 2, and largest will be Na plus. So our answer is option D. I hope you got that point. So whenever you are supposed to compare the ions, always positive ions are you are positive, you are having a lesser size. More positive oxidation state, lesser is your size. A very good question, in fact. Now, when we discuss about atomic size, the last thing we should know is the Lanthanide contraction. Why last thing? Because it is actually will be discussed in DNF block also, but because I've promised everything, I'm included. Whatever there is there corresponding to periodic table, I'll be discussing. Now, sir, what is Lanthanide contraction? We have beautifully seen the periodic table. Sir, the first transition series is scandium. This is fourth period, 3D series. This is fifth period, fourth period, 3D, fifth period, 4D. And this is the 5D. After lanthanum, till fourth period and fifth period, what can you say about size of, let's say, scandium and yttrium, or titanium and zirconium? Sir, down the group, what we say? Sir, down the group, atomic size increases. So atomic size will definitely increase. I'm writing with a different pen. Atomic size will definitely increase. So whose size will be larger? Titanium or zirconium? Sir, obviously titanium will be lesser in size, zirconium will be more than size, because, sir, down the group atomic size increases. What about the improvement of Z effective? You also have strong nucleus. Sir, I also have strong nucleus. So that factor is common for you also and me also. So that factor will be neglected for both of us, because both of us suffer from that strong nucleus. So if both of us are affected by that strong nucleus, then that factor is neglected that factor is common for both of us. So after that, who will play a part? Sir, periodicity. What is the periodicity? Atomic size should increase down the group. Why? Because your third shell is filled, my fourth shell is filled. So obviously 4 will be farther, so size will be more. So the basic trend is atomic size increases down the group. So among titanium and zirconium is of larger size. But after La, after this element number 57, the next 14 elements, that is from 58 till 71, are filled in 4F, F subshell. And hafnium has an atomic number of, remember, 72. So after hafnium till mercury, sir, nucleus has been increased by 14 protons. So if nucleus increases, so last electron is filled. In case of this 5D series, what is their valence shell that is getting filled? Sir, what is the shell that is getting filled? Sir, 5D. Maybe 5D. So, okay, I'm removing this over here. Last electron enter in. So let us say we are talking of 6th period. So the last electron will be 6th shell electron, maybe 6s electron. And the electron that you are filling over here is in 5D. So you can compare anything. Last electron enter in, although it will be a D block element, so last electron will be entering in 5D in case of lanthanoids. In case of elements after lanthanoids, elements belonging to D subshell but coming after lanthanoids. So electrons are filling in that period. So electrons are filling in the 5D subshell. But who will be their valence electrons? Are electron of 6s. So how will you compare the size from nucleus till 6s electron? But we know the shielding of these 4f electrons are not poor. They are very poor. The shielding is very poor. And because of this poor shielding, Z effective is not increased. It is drastically increased. In fact, more drastically increased than in case of D. Whatever we have seen, the poor shielding of D, this shielding is very poor. So if shielding is very poor, Z effective is increased drastically. And if Z effective is increased, the nucleus is very strong. If nucleus is very strong, then size will decrease. And what decrement you observe, what size decrement you observe, that it is not down the group, it should increase. So what decrement we observe in science, in nature, is their size is approximately equal to that of the 4D series element. So for example, if you compare size of HF and ZR, hafnium and zirconium will have approximately equal size. And why they have equal size? This complete reason is actually termed as Lanthanide contraction. This complete reason is actually termed as Lanthanide contraction, a very important point. Now, I have shown you this important point with proper photo. So, coming to a question of how this Lanthanide contraction questions are asked. So, this is a JEE mains question. Atomic radii of silver is closest to. So, silver is a 4D series element. Silver is a 4D series element. Silver is a 4D series element. And the 5D series element, which it just has below it, is gold. So atomic size of gold and silver will approximately be same because of this lanthanide contraction. Now, this is what we know about lanthanide contraction, and this finishes everything related to atomic size, which I feel is the most important property, because after this, whatever property we'll be studying, its impact will be we'll directly relate all those impacts with atomic size. So atomic size we have done thoroughly. Now moving ahead to the other property. What is the other property? Ionization enthalpy, ionization potential, ionization energy. It is simple. Whenever you have an element, let's say this element is M, it must be in gaseous state, because if it is solid or liquid, then if you give on energy, then first the physical states change. For solid becomes liquid, liquid becomes gas. So what NCERT and scientific community has done, that they have defined the ionization definition when the species is present in a gaseous state, and it should be isolated. I mean, it should not have influence of any other ion, because the interaction of charge will maybe excite electron. So it should be an isolated gaseous atom. Now what we have to do to this atom? Give this atom energy. So we will give this atom some energy. What energy will do? What we have learnt in atomic structure. The electromagnetic radiation having energy will come. Valence electron will gain that energy, and because of energy gain, it gets excited. And if it gets excited, it gets away from the nucleus, and such an atom is called an ion. So energy provided to an isolated gaseous atom, if that atom gains an energy, then the valence electron gets evicted from the atomic structure and you get a gaseous cation. So we very well know the enthalpy change. We are not supposed to calculate the absolute value as learnt in thermodynamics. So the enthalpy change of this reaction will be termed as delta H, because it's energy you are giving. So delta H will be positive. That means it's an endothermic process. And the amount of enthalpy change is termed as ionization enthalpy. Obviously, ionization enthalpy is always positive because you have to supply energy. Generally, you have to supply energy to that electron so that it may come out of the atomic structure, and the amount of energy supplied is called ionization enthalpy. Now, what will, let's say this ionization enthalpy is A electron volt. So what will be the corresponding potential? A volt, because we know potential is equal to work done upon charge. So work done, that is in joule, is equal to potential into charge. Now, this we have seen in atomic structure as well. So I'm just moving fastly. Now, what can you say about successive? Sir, when you remove one electron, like for example, let's say I have sodium. The isolated sodium atom, I'm providing energy and converting it into sodium cation. Okay, sir. So what is the enthalpy change of this reaction? This enthalpy change will be known as first ionization enthalpy. It will be named as first ionization enthalpy. Now, let's say now I have taken this Na plus atom, giving again more energy to it. It will form Na plus 2 and will give out one more electron. So the second ionization, the amount of enthalpy change to remove the second electron will be second ionization enthalpy. Similarly, the third will be third ionization enthalpy. So this delta H1, delta H2, delta H3 are actually termed as successive ionization enthalpy. And mind you, a very famous and important relationship that I'm going to give you, which is, if you talk of successive ionization enthalpies, delta H2 will always be greater than delta H1, irrespective of the, this is irrespective of the electronic configuration. Some people say, sir, sodium become Na plus is inert gas configuration. Yes, it is. Here the amount of energy may be, it will be very less. Very easily this sodium will become Na plus. So the amount of energy that has to be supplied, it may be very less. It may be 10 rupees. The amount of energy which will be required from Na plus to Na plus 2 to plus 2 will be, obviously, because this is inert gas configuration, so it will not at all try to go to Na plus 2. So here, if let's say for example it is 10 rupees, so it will be, let's say, 1 lakh rupees. Now if we try to remove one more electron from Na plus 2 and forms Na plus 3, that will be even higher. So my point is, when you are working with an isolated atom, let's say X amount of energy is used. When you are working with a positive species want you give electron to them. If you take out one more electron from them, they will always oppose and will oppose to a larger magnitude. That is, magnitude-wise, successive ionization enthalpies keeps on increasing irrespective of whatever is the electronic configuration. You should always keep this thing in mind. Very important conclusion. Moving ahead. Moving to the factors on which this delta Hi, that is enthalpy of ionization, depends, are quite simple now. First is definitely atomic size. Sir, how can you relate atomic size? We very well know, as atomic size increases, distance between nucleus and valence shell increases. So the ability to take out that valence electron outside will also be much easier, because as distance of nucleus from valence electron increase, it is much easier to take out that electron. So very less energy will be required. So as atomic size increases, the amount of energy required to remove that valence electron obviously decreases. So inversely proportional. And more powerful is the nucleus, more amount of energy is required. So this the periodicity is quite simple. So what is it? Sir, down the group atomic size increases. Therefore, because atomic size down the group increases, so this should definitely decrease. Quite easy. Just look at this graph also. From lithium to cesium down the group, atomic size increases. So delta H ionization value, you do not have to learn the value, but the trend. Lithium has got value of 520 kilojoule per mole, whereas cesium has got a minimum of 374 kilojoule. So down the group decreases. Trend you can very well judge. Now, along the period, sir, atomic size increases. Z effective also increases. So ionization, the amount of energy required to remove electron will also increase because atomic size decreases. Nucleus becomes more governing the valence shell. Hence, it is difficult to remove that electron. So, looking into the trend, sir, yes, we are very comfortable. It is increasing. Perfect. But the other factor, electronic configuration. If you just look at the graph, there is a dip between beryllium and boron. There is a dip in nitrogen to oxygen. Why so? Because ionization enthalpy, of a very famous example, because ionization enthalpy also depends on from which electronic configuration I am removing the electron. if that electronic configuration is stable. If that electronic configuration is stable, then my friend, it will be difficult for you to remove that extra electron. For example, this beryllium electron is removed from the 2s subshell. In boron, it is removed from the 2p subshell. This is a fully filled subshell, hence stable, whereas this is a partially filled. So, amount of energy required to remove electron from a fully filled subshell will be more. Hence, amount of energy required to remove electron from beryllium is 899, while for boron it is a dip 801. Moreover, one more thing you should keep in mind, that this 2s, for example, you have this 2s and 2p both are second shell electrons, but through n plus L rule, you must keep this thing in mind that for a same level of shell, 2s has more penetration effect, as in 2s is more penetrated inside the nucleus than 2p. So 2p is a bit farther, 2s a bit inside penetrated, as in closer to the nucleus relatively. So S penetration is slightly into the nucleus, then 2p. What about third shell? 3s will be slightly inside, then 3p, then 3d. So this penetration effect also you should keep this thing in mind, which is through n plus L rule, that because S subshell has lesser energy, so it is more stable, so more penetrated towards the nucleus. Although if you do not know that also, still you can feel this idea that it is difficult to remove an electron from a fully filled configuration than a partial one. Similar is the case with nitrogen and oxygen. Nitrogen has got stable half-filled configuration, so difficult to remove electron from nitrogen. Whereas for oxygen, because it is partially filled, it can be removed easily as compared to nitrogen. So again, for nitrogen and oxygen, there is a dip. For nitrogen, it is 1402. For oxygen, it is 1314. So this also you can clearly understand as a factor of ionization enthalpy. Moving ahead. Now let's compare the second ionization enthalpy of beryllium and boron. Sir, penetration of 2s is more, so it is more closer to nucleus. So removing electron from 2s subshell will be difficult. Moreover, it is fully filled, already done it. So because electron is removed from a more penetrated fully filled subshell, so first ionization enthalpy of obviously beryllium is more than that of boron, because this electron is partially filled also and of less penetrated subshell 2p. But question is asking you to compare second. So how to compare second? Remove one electron. So if this pink electron is removed, this is remained. If this pink electron is removed, this is remained. Now tell me, sir, penetration is same, both are 2s, okay, but it is fully filled and it is half filled. And moreover, if this one electron is gone, Be plus will attain, because then the inner shell will be coming into picture, which is inert configuration. Whereas this is a fully filled stable configuration. This is a fully filled configuration. So in order to remove the second electron, is electronic configuration answering you here also and over here also? So who will have more second ionization enthalpy? Obviously boron plus. Now moving to the next factor, which is also very important, the ionization enthalpy also depends on screening effect. We very well know this, sir. Screening effect was impacting atomic size as well. In the similar manner, you have to see this, like for the Lanthanides contraction that we have done, the 3D series titanium, the 4D series zirconium, the 5D series hafnium. Sir, we know down the group ionization enthalpy decreases. Why? Because atomic size increases. So because atomic size increase, nucleus become more far, the valence electron becomes more far from the nucleus, hence easier to be removed. So down the group, what are you expecting? Ionization should decrease. From titanium to zirconium, it is decreasing. Yes, sir. You do not have to learn the value. Just know the trend. So 658, 640, yes, sir, following the trend. But sir, we know lanthanide contraction we have done. Because of filling of that F block, Z effective is increased. And why it is increased? Because shielding of F is very poor. So shielding poor will increase Z effective, will increase ionization, as in energy required to remove electron, because now nucleus is interacting much more to the valence electron. Therefore, because size was same, but because of that shielding, size was same, was not getting increased. But what is the impact on this property? On ionization? Sir, it is increased. You can see the value. Almost in theoretical questions, what you can learn is like that is atomic size remains almost the same, whereas the ionization enthalpy of the 5D series elements are more than that of 4D. Reason is the same. Reason is the poor shielding of F electrons, because of which Z effective is increased. But the impact on atomic sizes, atomic size of 4D and 5D are almost equal, but ionization of 5D series elements is larger than that of 4D series because of the poor shielding. Now, one more application, the notorious group of P block, group 13. Just the same reason, before gallium, 3D is filling. So sir, because 3D is filling, Z effective is increased. So with the same reason, what was the impact on atomic size? Atomic size generally increases down the group, but for gallium and aluminium, there was an inverse relation. Gallium size was lesser and aluminium was more because its Z effective is increased. Although over there, we haven't seen such impact down, but we should see why. Sir, if you are taking that filling of F electrons, those F electrons are filled before thallium as well. Before thallium, apart from this, what we have seen, 3D, 4D, 5D, there is filling of, after lanthanum, there is filling of extra 4F, which is not happening in the above cases, because thallium is the 6th period element. So for thallium, Z effective is increased by a factor of 14. And shielding of F is much poorer than D. So Z effective of thallium is also much increased because of this filling of F subshell. But sir, this impact we haven't seen in atomic size. Yes, this is God's and nature's grace that this effect is still applicable, but its impact is not seen in atomic size. Therefore, in atomic size, I haven't told you about thallium because the periodic trend of atomic size was just the same, as in it should increase down the group and it was increasing. It was giving a variation in case of aluminum and gallium only. But in ionization enthalpy, this impact of filling of F subshell is creating an impact here also. Just look at the value. What are we expecting? Down the group, sir, delta H ionization down the group, because of increase of size, it should decrease. Let us check. From 800 to 577, it is decreasing, perfectly following. 577, 578, no sir. It is increased. But this explanation is the similar explanation for the atomic size which we have done again, that because of filling of D electrons, Z effective is increased. Now, after 578, 558, it should decreasing. But from 558 till 590, oh my God, sir, it is increased, and that too. This increase is less, this increase is large. Why it is increased? Sir, because of large increase in the nuclear attraction, that is Z effective. But this Z effective is definitely increased for thallium. But the impact in atomic size was not physically visible. But in ionization enthalpy, it is. So JEE loves this logic, and because I have given the value, so you should definitely tell me who, the exact order also you should know, because this is very famous example. So who is having the minimum value? The minimum value is possessed by indium. It is 558. Then more than 558, the second, the minimum is this. Then who is it is fifth. Who is coming fourth? Sir, 577, that is aluminium. After that, gallium. After that, sir, thallium. And who has the highest ionization enthalpy? Boron. So this is the exact order that you should learn as well. So just check and moving forward. So moving forward to the application size or side of ionization potential or ionization energy, let us revise this, that ionization value decreases in magnitude down the group and obviously it increases along the period. So basically the S block elements that we have in our periodic table, they have very low value of ionization energy or ionization potential because it is increasing along the period. So because they have a very low value of ionization potential, therefore these are metallic in nature, as in they have a tendency to give electrons, like our S block elements, the alkali metals. Similarly, when we move along the period, because ionization is higher, that means the nucleus is holding up those electrons and is not ready to give them give those electrons. So obviously the nucleus is willing to gain electrons, so they gain non-metallic nature. So the non-metallic nature, obviously those who have high value of ionization enthalpy, like our p block elements, and mostly the 17th group, those are halogens, they will be having non-metallic nature. This is the very basic and first application of this value. Now coming to the second application, which is reducing character. Now mind you, what is reducing character? If I am an reducing agent, I will reduce others. If I will reduce other, I will oxidize myself. And if I'm oxidizing myself, as in ion, oxidation means loss of electron. So who will lose electron, who will have a higher tendency of losing electron, will be good reducing agent. So who has tendency to lose electron easily? Sir, metals, as in the S block elements, as in who has less value of ionization potential. So obviously the 1A group, that is the group 1 elements like Li na ki rab se faryad, not taken radioactive. So obviously in gaseous state, mind you, we are speaking of gaseous state, sir. Down the group, ionization further decreases. So who will be a better metal? Sir, obviously cesium will be a better metal, and among them lithium will be least metallic, because having the relatively among S block element, lithium has highest ionization enthalpy because of its small size. Now, but this reducing character we have discussed was in gaseous state. Coming to the aqueous solution, the ionization whole soul do not decide. Then sir, why doesn't it decide? Now it is actually a p block element concept, but discussing. Now whenever a solid metal wishes to give electron, it is not actually a single step process, it is a 3-step process. The first step is, first the atom has to get sublime, that is its solid has to be converted into gaseous state. So the first step will be the involvement of sublimation enthalpy. Now, once this isolated gaseous atom is formed, now the energy will be provided and the gaseous cation will be formed. This is the value of ionization enthalpy which we are considering. Over there in gaseous state, we have considered only this thing and marked the trend that cesium was having the highest reducing power while lithium was having the lowest. But over here, first step is sublimation, second step is ionization, and now the gaseous ion, don't you know or don't you feel that the electron transaction takes place largely in aqueous medium, in solvent? So can't you understand this, or don't you make this feeling, sir, gaseous ion has to be dissolved in solution, and this dissolution requires their hydration. The amount of enthalpy change when 1 mole of a gaseous ion is dissolved in solvent, and mostly the solvent is water, so this is called hydration enthalpy. Now actually the first step that we have considered over here is definitely an endothermic process. The second step is also an endothermic process, because in these two processes, energy is required. They'll take energy. But this hydration is actually an exothermic process. So who wins the race is decided by these three processes. And as we very well know, if we add up these three reactions, these things will get cancelled. And what is left, sir? M solid will give M plus aqueous, and then it will lose electron. So the overall delta H, as we know from thermodynamics, it is equal to this plus this plus this. So if a solid wants to actually give electron in aqueous condition, this overall delta H has to be more and more negative. Why negative? Because basic common sense I'm trying to make you understand over here. If I as a solid want to proceed forward, I should feel stable. And if I should feel stable while doing so, while being an aqueous ion, then if I'm stable, my energy must be reduced. So if my energy is reduced and this solid form has a higher energy, where the extra energy is gone? Extra energy has to be released. So actually, which is the energy releasing step? Hydration step. Therefore, this in aqueous condition reducing character is largely decided by the hydration enthalpy. And which ion gets hydrated easily? We will be discussing it in chemical bonding also, but the basic is very important, so I'm telling you this also. Actually, the hydration enthalpy, delta H hydration, depends upon charge density, which is charge upon size of the ion. Largely it is decided by charge first, so this is dominant, and if charge is common, is same, then size decides. So an ion having higher charge gets heavily hydrated, and if charge is same, then the ion which is smaller in size gets heavily hydrated, because size small, hydration high. Now if you talk of the alkali metals, who has got the smallest size? Lithium, because charge is same for each of them. And because lithium and all in fact second period elements, they are not small. As compared to the further groups, second period elements are smallest. So because of smallest size, their hydration is highest. Therefore, these all three steps is decided. In order to account for all these three steps, we calculate their electrode potential. And while understanding their electrode potential, as an electrode potential is their reduction potential. So by actually experimentally seeing that value, so this is also a fact for us, but these basics are also important. So lithium becomes, in gaseous state, if you see, lithium was the lowest reducing agent, but in aqueous condition it wins. And why does it win? Because of its maximum hydration enthalpy. But the exact order you should learn. So lithium being highest, potassium, rubidium almost have equal reducing power, lesser than lithium, but greater than cesium and cesium and sodium, while cesium comes later and least is sodium. A very important point, a very important fact you should know, although the detail behind it I've already discussed. Moving ahead. What is the other, now talking about the reducing character, sir, metal have tendency to gain electron, but those in the moving along the period who has high value of ionization enthalpy, the group 17 elements, sir, they are non-metals. They have high value of ionization enthalpy. So that means they do not wish to give electron. In fact, they wish to gain electron. And if you want to gain electron, you are getting reduced. If you are getting reduced, then you will be oxidizing others. So 7A of the Mendeleev's periodic table and 17th group of the modern periodic table, that is halogens, have maximum ionization potential. And therefore, we can say they are strong oxidizing agents. And thank God, because Mother Nature, talking about the oxidation power, although while oxidation also, there is process. This is not only a one-step process, because ions have to give electron in aqueous condition also, but that is largely decided by their ionization enthalpy only. If I am an oxidizing agent, I will oxidize others and I will reduce myself. Who will reduce itself? Who will gain electron? Who will gain electron? Who has the maximum value of ionization enthalpy. Who has maximum ionization enthalpy for halogens? Sir, fluorine, because down the group it decreases. So who wants to gain electron to the maximum extent? Fluorine. And hence fluorine becomes the strongest oxidizing agent while iodine becomes the weakest oxidizing agent. Moving to the last application, stability. I'll show you in questions. Actually, whenever difference of okay, because delta only we represent as difference as ionization. So the first ionization enthalpy and the second ionization enthalpy, it may be other also. You can calculate the difference between these two. Similarly, for third and second, for fourth and third. So for the successive values of ionization enthalpy, if you mark and see their difference, you can easily say what is the stable oxidation state for any element. Why? Because we very well know successive ionization enthalpies goes on increasing. But whenever they will increase, but whenever the increment is large, then we say because increment is large, so taking out that extra electron is taking too much of efforts. So whenever that increment is increased drastically, then we understand no. The previous oxidation state was its stable oxidation state. So you can very well identify the stable oxidation state of any element by just marking the difference in values of ionization enthalpy's difference. We will see because those questions are even asked by JEE. Moving ahead. Now, let us discuss some questions regarding ionization enthalpy. Very easy questions are asked, but I have discussed everything which you should be knowing. Moving ahead. This is a 2024 JEE mains question. You have to tell me the correct order of first ionization enthalpy. Okay, sir. Among whom? Sir, this we have already done. Oxygen, nitrogen, beryllium, fluorine, and boron. Along the period, ionization increases. So, who will have highest? Fluorine. Fluorine is fourth. So, fourth will be highest. After that, sir, oxygen, nitrogen. But nitrogen has stable half-filled configuration. So, nitrogen comes first, oxygen comes later. Nitrogen is second and oxygen is first. After that, beryllium, boron. Along the period, it increases. So, boron must have highest, but beryllium has larger delta H ionization than boron because beryllium has stable fully filled 2s2 configuration. Moreover, the penetration of 2s is more. Remember that boron beryllium trend was asked. So what comes next is beryllium and then boron. Boron is 5 for us, beryllium is 3 for us. So answer will be 5, 3, 1, 2, 4, Bombay. Moving ahead. Next question says you have to tell the correct order of increasing ionization energy. Now, increasing ionization energy, sir. These belongs to similar group. Okay. Beta, mange, car, scooter, bap. Okay. Scooter is not asked, so I just draw barium. Now, in the same period, the sulfur comes post calcium. So sulfur will be somewhere here. Usse, selenium is just beneath sulfur. And then argon. Argon is somewhere here. Now, why I'm drawing like this? Sir, periodicity. Down the group ionization decreases. So among calcium and boron, calcium has more ionization. Barium, not boron, barium. Barium has lesser ionization because it decreases down the group. Just check these in the options. Calcium should have higher. This is saying calcium lower, wrong. This is saying calcium lower, wrong. This is saying calcium lower, wrong. See, just by checking calcium, barium, we have got the answer to be C. You can definitely check for sulfur, selenium. One thing is argon. Sir, it is an inert gas. Why it is said inert? Because it will neither lose nor gain electrons. So its ionization will be much higher. Hence, argon will be having the highest. All options are saying that only. Moving ahead, again, the first ionization enthalpy you have to compare now. Among Li, Na, Ki, Rab. So they are alkali metals. For alkali metals, ionization decreases down the group. So among them, who will be having highest? Sodium. But I'm comparing sodium and scandium. Scandium, let us go. Sodium is a third period element. Sodium is a third period element. Post sodium, potassium comes, and after potassium, calcium, and then scandium. Although you are only required to compare them. Now, what I'm telling you is, sir, down the group it decreases, but along the period it increases also. Na? So whenever you have just beneath your group, but down the group it decreases, but along the period it increases also. We know this. So because increment is not till calcium, increment is still scandium. So this was a tricky question, but I'm telling you this, that whenever you go just one step down and then you move forward, so when you compare these two elements, the later element of the next period generally wins. Like over here, scandium has the highest ionization enthalpy among them. So this is your answer. That's why I've included this question as well. A nice question. Moving ahead. Now, the difference thing that I was telling you. Now, you are supposed to calculate the ionization. Now, the values are given. Sir, how to calculate? Just what we have done. These are nothing but second period elements. For second period elements, this is electronic configuration of nitrogen. Sir, half-filled configuration. Half-filled configuration will have the highest value. Then before that oxygen comes after nitrogen, but because of half-filled configuration it attains maximum. So oxygen will be coming second. So what is the second best? 13, 14. This is beryllium and boron. Obviously we know boron, this 2p1. So boron is 801. Why? Boron loses. Boron has lesser value of ionization. And who has higher value of ionization? Beryllium. So P is 2. So P is 2, P is 2, P is 2. Only one option has P is 2. So directly answer A. Moving ahead. Now the difference question that I was telling you. Now you have to tell that the element, the number of valence electrons. Sir, valence electron? That means number of outermost electron. If I keep on losing electron, the outermost, I'll attain an inert configuration. And once that inert configuration is attained, now I will not lose electron. And if you still try to take away that electron, it will be having a very large energy. So by looking at the electronegativity change difference, we can very well predict that what will be the number of valence electron, because that oxidation state will become stable. Giving you example, it was a JEE question also. Many questions of this sort have come. I have just picked up all the type of questions for you. Now, from 800 to 2400, almost 4 times, we are just observing the pattern because successive value increases. You just have to observe the large increment. So this is 4 times, okay. Now this is not even double, because 2400 is double is 4800, so 1.5 times, but still successive is increasing. Now, after that 3600, what is coming? Oh, 25,000. You can clearly see, visually see the large chunk of differences happening over here. So, this element is comfortable in losing how many electrons? 3. The 4th electron, when it is losing, it is requiring so much of extra energy. Therefore, the number of valence electron will be 3. So, its maximum stable oxidation state will be plus 3. So number of valence electron will be 3 over here. So your answer is beautifully 3, a very good type of question actually. Now, coming to the next property, which is electron gain enthalpy. Now, similar to that of ionization enthalpy, on the contrary, you can think of electron gain. How? So whenever an isolated gaseous species accepts an electron, like over here, fluorine, an isolated gaseous atom, is accepting electron and forming an anion. During this process, obviously, nucleus will have a huge tendency to gain that extra electron. And while gaining that extra electron, there is generally always some amount of energy released. Hence, the enthalpy change of such a process is termed as delta H Eg. That Eg represents electron is gained. And it is obviously generally an exothermic process, so energy is generally released, not always, generally. So what is electron affinity, sir? Mathematically, whatever enthalpy change that has taken place, the negative of that value. So electron affinity is nothing but it is in magnitude equal to electron gain enthalpy, but with an opposite sign. So speaking technically, both are mathematically, they are different. How they are different? Because EA is equal to negative of delta H Eg. But going by the trend, sir, whenever an isolated gaseous atom accepts an electron, the enthalpy change is called electron gain enthalpy. Like in the other example, nitrogen is also an isolated gaseous atom. When it is gaining electron, the enthalpy change is still called electron gain enthalpy. But as you can see, this value is positive. So generally it is negative. Sir, why it is positive over here? Because we very well know there will also be some factors like we have already seen in ionization enthalpy, the electronic configuration of nitrogen is half-filled stable configuration. So it do not want to disturb. Therefore, it is not having an affinity to gain just one electron because it will be disturbing its stable electronic configuration. Hence, for nitrogen, this value is delta H is positive. So electron affinity is minus of that value. Moving forward. Now, obviously, we have looked into the factors, but let us summarize them. So with atomic size, how can you relate electron affinity? If I'm saying electron affinity, I am meaning electron gain enthalpy because I'm comparing the magnitude. We very well know the sign will be opposite. So electron affinity or electron gain enthalpy. I'm speaking for both, but I'll be writing one, sir. As atomic size is decreased, distance of nucleus and valence electron decreases. So the incoming electron will also be entertained more. Therefore, as atomic size decreases, electron affinity will go on increasing. So there's a inverse relation. Similarly, for screening, if you are shielding or screening the attraction between nucleus and valence shell, the incoming electron will also feel less attraction from the nucleus. So more be the shielding, lesser be the affinity of that atom to entertain that extra electron. What about effective nuclear charge? More is stronger is the nuclear charge. More will be the electron affinity. Now this I am removing because this proportionality should be here. Now, sir, obviously we can predict the periodicity. It will be same as ionization enthalpy. So what will be the periodicity of electron gain enthalpy? Down the group it will decrease and along the period it will increase, just opposite to that of atomic size, because from atomic size it has an inverse relationship just like ionization enthalpy. Now, some important points to note. Elements like helium, neon, argon, because they are inert gases. Sir, inert gases have actually, these inert gases, they actually have no affinity. Why they will want to destabilize their stable electronic configuration? Therefore, they do not want to, their affinity is zero. What theoretically it is said that their affinity is zero. But if you do the experiment, every non-spontaneous processes can also be forced to take place. But when you are forcing inert gases to take electron, they will not do by themselves. You have to endothermically, you have to provide extra energy, excite their electron, and then if you will be very vigorous in doing something, obviously you will supply energy and you will do that non-spontaneous job, but it will be a non-spontaneous job. So delta H Eg value will be positive. That means energy will not be released. You have to supply that extra energy so that electron may be excited. It will create an empty space, and in that empty space you are forcefully adding an electron. The atom is not having an affinity. Similarly, as I've already told you, group 15 elements, the nitrogen family, they will also have very less affinity very less affinity, or maybe you can say zero affinity, because their value is also positive. But point is, nitrogen is the smallest. For the elements coming below nitrogen, the other group 15 elements, the value is not always positive. So that's why I've written very less. So that's a theoretical point you need to remember. Now, what about the metals, sir? S block elements, precisely the group second alkaline earth metals, they also have very less affinity, and their delta H Eg value is also positive. So very important point to note. Now let us explore this table of values of electron gain enthalpy for elements. As we very well know, down the group, electron gain enthalpy value decreases, as in it is energy released, so will be negative, but magnitude will decrease. So for hydrogen, it is minus 73. For cesium, it is minus 46. So who is becoming more happy and releasing more energy? Hydrogen. So who has high electron gain enthalpy? Hydrogen. 73 rupees it is spending. But cesium is spending only 46 rupees when electron is coming. So obviously, electron gain enthalpy is decreasing down the group, because you have to check the magnitude. Minus sign shows that energy is being released. But why I'm showing you this trend is because, sir, we feel electron gain enthalpy decreases down the group. So technically, who should have the highest? So obviously, the element at the top. Like over here, hydrogen is having the highest. But actually, when you go to the second period elements, hydrogen was not showing this case. What case? Which I'm trying to explain you. A very important point which JEE loves asking is, you are seeing this picture also, that note the trend. But let me first tell you this. Before noting that trend via values, I'm giving you a basic. Technically, who should have maximum electron gain enthalpy, let's say in p block element among halogens? Sir, the top one, fluorine. No. Not fluorine. In fact, chlorine has highest delta H Eg value. Not oxygen. Sulfur has highest. Not nitrogen. Phosphorus has highest. Not aluminium. Not boron. Aluminium has highest. That is, second period element are supposed to have the maximum electron gain enthalpy, but they are not having the highest in their respective group. The element just beneath them are having. This is a periodic fashion for each and every second period element. Why is it so? Their Z effective is very large. Their Z effective is large. They want the electron to be introduced in their atomic structure. The nucleus definitely wants the incoming electron to please come and please visit my valence shell. But the already existing electron, because size of second period elements are very small, therefore the already present electron, when they will see to this electron coming, they will repel the incoming electron. Nucleus is attracting that electron with great extent. But because of unavailability of space in the home, the nucleus of the family, your father, your grandfather wants to invite his friend like anything to his home for dinner, for staying for a week or for a month. But because the house is having just one room or two room, so accommodating that friend of your father, the already present family members will be repelling so much that nucleus and overall effect will not be such enjoyable. So actually point is, nucleus want that electron to come, and because the nucleus wants, so it will be releasing large chunk of energy because getting stable. But most of the released energy is now utilized to excite the already present electron. Therefore, the overall result what we see is the amount of energy released is not that much high, because large chunk of that energy is utilized to excite these electrons, and therefore I've written the complete theory for you. Therefore, instead of fluorine, chlorine has highest delta H Eg among group 17. Similarly, for other elements, you can very well see. That's why I was showing you this graph. Fluorine is having a value of minus 328, whereas chlorine has minus 349. Chlorine has got larger delta H Eg. Similarly, sulfur is larger than oxygen, phosphorus is larger than nitrogen. Nitrogen, I've already told you, because the configuration is very stable and because now we know size small, so incoming electron will be repelled by the existing electrons. Therefore, although other group 15 elements have negative value of delta Heg, but nitrogen has positive value of delta Heg. Now, these alkaline earth metal, alkali metal follow the trend, but alkaline earth metals, they have no affinity to gain electron. Therefore, their delta Heg value is approximately 0. Now, there I want you to learn some trend also. See, oxygen from 16th group only I want you to learn. For 16th group, what is the trend? Sir, it is decreasing down the group. Who has highest? Sulfur. Oxygen has lost the battle of getting the most delta Heg negative value. It has lost the battle from all of the group members. Its delta Heg value is even lesser than polonium. So this is the exact order is also the value you should not learn, but the exact order is very much loved by JEE. So what is the exact order? Exact order tells you that delta Heg value obviously decreases down the group. For group 16, oxygen loses this battle and oxygen loses from all. So oxygen will come at the last because this is 174, oxygen is 141. Now, what about halogens? Fluorine loses the battle, but only from chlorine. Fluorine delta Heg value is greater than bromine and iodine and astatine. Look over here. This is 324, this is 328. So fluorine lost the battle of having that highest delta Heg value. But fluorine only loses to chlorine. To other members, fluorine won. But for that, you have to do not learn the value, but learn the trend. And what about inert gases? These exact data, they have positive, but what is the order which has highest positive? Neon. So for this, I'm giving you a trick how to learn who has the highest neon. And what are you supposed to think and learn for inert gases? Sir, they do not follow any order. So for every element, what is the trend? It decreases. So for them, we are learning, we are memorizing the trend as it is increasing down the group. This is decreasing. So for group 18, it is decreasing. For group 18 also, I beg your pardon. For group 18 also, it is decreasing down the group. Just do not see helium at first. It is decreasing from second period. So neon will have the highest value and then it is decreasing. Just check 116, 90. Argon and potassium has approximately equal value, then decreased. And again, who has the first one has lost the battle from all. So helium will be coming at last. So what will be your trend? Hai at the last, na argar kar 0 run pe, where argon and krypton has equal value of delta Heg. So delta Heg trend decreases down the group. For inert gases also, although it is positive, we are learning it is also decreasing. How we are learning? By the value. So not learning the value, but learning the trend. So whatever trend is follow of delta Heg, inert gases also follows the same trend. Oxygen loses its battle from all. Helium loses its battle from all. And the rest of the trend goes the same. So this is how you can learn, because the exact trend was asked. Moving ahead, this we have done. Now, some people say electron gain enthalpy is always negative. No. Obviously, it depends upon the electronic configuration, which we have seen it is negative for most of the elements, but not for all. And one more thing, the first, like successive ionization enthalpy, similarly successive electron gain. Once a neutral gaseous atom gains an electron, some energy is released, that is delta Heg1. But after this release of energy, this neutral atom has become a negative ion, an anion. My dear friends, an anion, a minus, has an affinity to attract plus. If you try to take one more electron, if you try to give electron to that ion, minus will repel each other. So you have to do it again forcefully, because that minus species do not want to gain one more electron, because minus always repel each other. That's why this minus, when again getting an electron, this is always a second electron gain is always a endothermic process. This is also a very famous question. So why it is positive? The question is asking because O minus ion will tend to resist the addition of another electron because minus minus repel each other. Moving ahead. Now, now one very important logic. JEE has asked this too many times. I've just summed up all the questions for you. Sir, ionization potential. Let us say you have sodium. Okay, sir, we have sodium. This is sodium. You are ionizing this sodium. How will you ionize this sodium, sir? We will remove one electron from sodium. Okay, remove it. Sir, every process is reversible. So can you think of the reverse process? Yes, sir, definitely. What will be the reverse process? Sir, Na plus will be gaining electron. So if this process, if to the pink side of process, I have said this is delta H ionization of whom? Of sodium atom. Then can I say that the reverse process is delta HEG as an electron gain process of the formed cation of sodium cation? Yes. So actually, delta H ionization of sodium is by magnitude. Obviously, this is an endothermic process, so this will be exothermic. If this side energy is absorbed, then for opposite reaction, energy will be released. Okay, it may be spontaneous or not. If at all it is happening, then if it is taking energy, then if you want to come here, you have to release that amount of energy. Now, so electron gain of Na plus will be of similar magnitude. If 100 rupees has been given to sodium and it has formed this, so it will give back that 100 rupees and will come back. Easy. So ionization potential of sodium will be electron affinity of Na plus. Option A, very important point, asked too many times. Now again, okay, now taking a question. The question says which of the following? Now the question says which of the following have most negative electron gain and least? Sir, this we very who has most negative? Sir, electron gain enthalpy increases along the period. So who will be having, sir? Those before inert gases, group 17. But fluorine loses the battle. So who remained? The topper, chlorine. So chlorine is given. Now fluorine has lost but fluorine just loses from chlorine. So who will be having least? No. Fluorine will only lose from, so it will be having the second largest electron enthalpy. So not least. Now, phosphorus and sulfur, just draw the periodic table. So sulfur, then comes chlorine, then here is fluorine, and before sulfur we have phosphorus, and we know delta HEG along the period, delta HEG increases. So phosphorus and sulfur, who will have high value of delta HEG? Sulfur. So between phosphorus and sulfur, it will have a lower value through periodicity, simple. So phosphorus will have the least value. First, they are asking the most. First is chlorine, okay, and least is first is chlorine, okay, and least is phosphorus, okay. So you have option D. I mean, you have to practice question to do them fastly. So practice is your set piece of cake, so you should do it. And I'm discussing all the type of questions for you now. Positive electron gain enthalpy, sir, we have already learned. Although we know this is positive, but down the group, it follows the same trend of periodicity, as in it decreases. Just helium loses the battle from ore. So it should decrease. So who will have highest? Highest will be attained by neon. Hai na argar kar zero run pe. So this is right because helium has lost the battle, and this is the same trend. Hai na argar mein AR they have not given, but chromium, krypton they have given. Both have equal. Zero is xenon, run pe radon not given, and helium at the last. So this is your answer. Told you, if you do not know the trend, this is also a question, an asked question, and very probable because NTA has to repeat patterns. Now, coming to the last property, electronegativity. Now, it is very easy because we have already discussed electronegativity in a sense. Why? Electron gain is what you are actually taking an electron. Electronegativity is basically defined for atoms when they are associated in a covalent bond. Like for example, if this is an atom A and this is an atom B, and they have formed a covalent bond. Because electronegativity is not a property, you cannot calculate it, it's a tendency. So this line is small or big, you cannot say unless you draw another line. So now this yellow line, when compared with this pink line, it is small, but when compared to this white line, it is big. So what is my tendency? My tendency of attracting electron. Okay, even the name suggests electronegativity. So my tendency to attract electron. But my tendency to attract electron will depend upon with whom I am playing the game with. The game where electronegativity definition comes into play is the game of forming a chemical bond. So whenever a covalent bond. So whenever a covalent chemical bond is formed, the shared pair of electron, the center of mass, if both have same electronegativity, now this term is utilized. If both have same electronegativity, let's say this molecule is a non-polar molecule like hydrogen, the center of mass of the shared electron will be at the center. Nobody has taken up. It's a perfect sharing. Like there are two partners and shared the equal share of money, exact 50% share of money, but if these atoms are not similar, one must be having a heavy proton, a strong proton, a strong nucleus. Proton, what does proton do? Makes the nucleus strong. So if my nucleus is strong, I'll have more attraction for those electrons. So I'll have more attraction for the shared pair of electrons also. So let's say if B is more electronegative, it will attract a large chunk of this shared cloud towards itself. But because it's a covalent molecule, it will not take complete electron. If it will take complete electron, then this will become a ionic bond and it will not be termed as a covalent molecule, then it will be an ionic molecule. So let's say if B is more electronegative, so B attains a partial negative charge while A attains a partial positive charge. Why partial? Because some of the electron cloud is attracted by B, not the complete cloud. If the complete electron is transferred, then it will become complete -1 and it will become complete +1. Like HCl is a polar covalent molecule where chlorine has got delta negative and hydrogen has got delta positive. When this electronegativity difference increases very largely, like for NaCl, we don't write NaCl like Na bond Cl. We just write Cl minus and Na plus because here the complete transfer of electron has taken place. And why it has taken place? Because electronegativity difference is large enough. So electronegativity difference has find its application as a tendency. It is not a property. And what tendency electronegativity is? The tendency to gain a shared pair of electron towards itself. Now, it's a tendency. It has no unit because it is a relative strength. And electronegativity is a property of a bonded atom, For ionic compounds, generally electronegativity is not used. I mean, they found their application in covalent molecules only. So energy will be liberated. So it is saying electronegativity is a property of a bonded atom, not an isolated gaseous atom. So no energy will be liberated nor absorbed because you cannot exactly quantify like the value of delta H Eg, delta H ionization. Those are exact enthalpy values which can be thermodynamically and experimentally that values can be calculated, but electronegativity is a tendency. So sir, how will you gauge this tendency? Our scientists have developed some scales. The first scale is the most famous Pauling scale. Now, although I have given the formula, but I do not wish you to learn this formula. For JEE mains, you can completely skip, sir, then why you have given this formula? Just for the sake that whenever you land up for a question, maybe for advance, then this slide will be more than sufficient for you. So, sir, this is a scale. Yes. What we have to know about this scale? This general point. What is the general point, sir? What is the trend of electronegativity? Just same as electron gain and ionization, because as atomic size decreases, distance between nucleus and valence shell also decrease. So nucleus will become dominant, and what nucleus wants? It wants electron. So electronegativity increases along the period and decreases down the group, just like electron gain enthalpy and ionization enthalpy. So the trend is similar for all of them. Now, because we know this, can you tell me what is who will be the highest electronegative element? Fluorine. But sir, fluorine lost the battle from chlorine, because in that case, actually the electron was coming. Now, if there is a bond between H bond F, F will attract a shared pair of electron towards itself. But F do not have to bring that electron to the house. So point is, during electron gain, because actually the electron was coming to the atomic structure of fluorine, and because it is very small, therefore fluorine was feeling not very comfortable. When it is covalently bonded, fluorine do not have to bring this extra electron. So it is a tendency, and because this extra electron is not coming to my place. So my house, for example, your father has invited your his friend to the home, but actually the friend is not going to come. Then who will be feeling more relaxed and more comfortable and more morally correct? I'm inviting my friend, your father. And because actually when his friend is coming to your place, and the basar, the unbalance that is happening in the family, it will happen when the friend will actually come for a month. So similarly, because electronegativity is a tendency, therefore that electronic repulsion problem is not created, because actually the electron have not even come. It is just a tendency of sharing the shared electron cloud. So definitely fluorine will invite, come. Therefore, fluorine is supposed to have the highest electronegativity, and in Pauling scale, this value is 4.0. The second largest electronegative element is oxygen with a value of 3.5. The third largest is both nitrogen and chlorine, both have same value of 3. Now, do I wish you to learn this value? Yes. The values of Pauling scale which I have used are important. So, after this, but I'm giving you a trend also. For second period elements, you can very well see the difference is 0.5, 0.5, 0.5, 0.5, 0.5, 0.5, 0.5. You can very well write them, and for these three, you should learn. Fluorine 4, first. Oxygen second, 3.5. Nitrogen and chlorine third, 3 each. For second period element, start reducing by 0.5. Now, electronegativity decreases down the group. So lithium, let's say, has 1. So it should decrease, as in the below one should has lesser and the higher one should have higher. For hydrogen also, you should learn the value is 2.1. I'm giving you a trick. For hydrogen, it is 2.1, and the trick that I'm giving you will be for carbon and its members. There are few elements like nitrogen and chlorine has same value. Nitrogen and chlorine has same value of electronegativity in Pauling scale, that is 3. Similarly, cis, CIS. In organic chemistry, you learn cis trans. So cis, CIS also have electronegativity of 2.5. So this is how cis will be very much used by you. So CIS, if you learn this. So 3, electronegativity decreases down the group. So iodine, bromine is above iodine, so it will be larger. So it is 2.8 and it is 2.2. What is the difference? 0.3. 2.8 higher, 2.2, 0.3 higher, 0.3 lesser. Just a way to remember, or else it is 2.8 and it is 2.2. You can very well see astatine, although coming at the last, down the group electronegativity decreases, but still astatine is having a value which is much larger than phosphorus. So there are certain important value trends that you have to learn, and whatever I have written, you should learn them. Now, from sulfur, we know from cis it is 2.5. Now, over here it is 2.1, as in difference is 0.4. After this, 1.8, difference is 0.3. Now the difference will remain 0.3. 1.5 less, 0.3 less, 0.3 less, 0.3 less. So we reached till here. Hydrogen is 2.1, and obviously electronegativity increases like this. So first group will have the minimum electronegativity. Moreover, it decreases down the group. So who will be having the lowest electronegativity? Cesium. Why not francium? Radioactive substance we do not consider. Moving ahead. So these are some values which you should learn You will directly end up question. This is also a April 2023 question. Exactly whatever we have learned, the Pauling scale, you can attempt it. I have written the values also. So you will be able to attempt these questions only when you know the exact trend, hence given. Now, there are multiple scales. Obviously, Pauli was not the only one made that scale. There are multiple scales, not good for mains. So just given them for your future references. Although Millikan used a common sense only. Electronegativity is the similar property. The trend is similar, just like electron gain and delta H ionization. So he said you take the average of both of the two, whatever value you will get, that will be defined the electronegativity. But it is not very famous, but still. Then again, an Alfred-Roschow scale, it used the Z effective calculation and the distance of nucleus from its valence shell, that is the radius in angstrom. But just giving you a glimpse, you don't learn these formulas. Now, this is the most important thing. I mean, one of the most important thing. Now, after this, let us move to factors affecting electronegativity. Sir, periodicity we have seen. So as atomic size increases, distance from nucleus and valence electron increases. So it will be less effective by the nuclear charge. So as atomic size increases, ability to gain electrons, so ability to be electronegative obviously decreases. So atomic size and electronegativity are inversely proportional. What about effective nuclear charge? More strong is the nucleus. Nucleus wants to attract electrons. So more effective nuclear charge, more is your electronegativity. Now, hybridization state, a very important point. We will be taking it in chemical bonding as well, but doing it here also. Like here, I'm talking for carbon. Basically, I'm talking for carbon because organic chemistry is all about carbon. Sir, carbon electronegativity, we know. Sir, carbon electronegativity through cis we have learned it is 2.5. But this carbon electronegativity that you have learned, when you go to organic side of chemistry, that carbon is a alkane, a sp3 hybridized carbon. What is sp3 hybridized carbon? Alkane. As carbon start forming multiple bond, the hybridization changes. We'll discuss. But all of those who know, or else I'll be discussing in detail in chemical bonding. Alkane is an sp3 hybridized carbon, and that carbon is supposed to have a electronegativity of 2.5. As hybridization becomes sp2 and sp,s character increases, and through atomic structure and periodic table, now we know penetration of s is closer to the nucleus. What does nucleus do? Nucleus attracts whom? Electron. Attracting electron property is called electronegativity. Sir, if s character increases in any orbital, nucleus dominance will increase. It will be more and more closer to the nucleus. And if I'm more and more closer to the nucleus, nucleus will have demand for extra electrons. So electronegativity increases. So the thumb rule is S character is directly proportional to electronegativity. In sp3, how many orbitals have formed this hybridized orbital? 4. Out of them, s is 1. So contribution of s is 1 by 4. That is 25%. In sp2, contribution of s is 1 by 3 because total 3 orbitals are used to form sp2 hybridized orbital. So contribution of s is 1, total is 3, 1 by 3 is 33%. 1 by 2 is sp hybridized orbital has an s contribution of 50%. So s character increases, electronegativity increases. Therefore, sp hybridized carbon is not the basic carbon that you know. That basic carbon is carbon of an saturated alkane. Now, coming to oxidation state. Generally, we know through ionic equilibrium, I'm repeating it again. What is actually an acid? Sir, acid is a substance which has a tendency to gain electron. Now, coming to metal and non-metal, who has tendency to gain electron? Non-metal. So, generally, non-metallic compounds form acidic oxides because most of the questions that are served to you are of oxide because oxygen reacts with every element. Every element. Now, if an element is forming an oxide and if it is a non-metal, so non-metal oxides will be acidic. Similarly, base tendency is basically to give electron. Who has a tendency to give electron? Metals. So oxides of metal will be largely basic. And if I'm a metalloid, I will land up being an acid also, being a base also. So I'll be called a metalloid or an amphoteric oxide. What is a neutral oxide? Which react neutral. I do not react with acid also. I do not react with base also. Now the question of oxides are always famous for JEE. Some people say, sir, metal oxides are always basic. No. Because sometimes if oxidation state of a metal is increased to its maximum extent, then I have a tendency to give money to everybody. But when I have given to that friend also, this friend also, that friend also, I have given loan to everybody. And now nobody is returning my loan. So now I want money, I want electron. Similarly, when oxidation state of metal increases, they start becoming acidic because they have reached to their maximum capacity of giving. Now they are they have attained too much of positive charge, and now this plus will attract minus. And attracting minus is called electronegativity. So electronegativity is directly proportional to oxidation state. For example, although these are all metals, but when manganese is in maximum +7 oxidation state, it will become acidic. In +4, it will be less acidic. In +2, it will be least acidic. So this is order of acidic nature. Similarly, for the oxides, so non-metal is anyway, non-metal anyway has a tendency to gain electrons, so it is more and more acidic. But if non-metal attains positive charge, it will be drastically acidic. My neutral tendency is also to gain electron. If by any means I have given electron to anybody, so I'll attain a positive charge. So O+2 will be highly acidic. Most acidic, and O2- will be least acidic because whatever electron I need, I have already got them, so I will be least acidic. So these are all acidic orders. Similarly, iron is a metal. Iron +3 is most acidic. In neutral state, it is obviously very less acidic than Fe+3. A very important point, you will see so many questions on this. Sir, if an oxide goes to water, it forms hydroxide. If oxide was basic, hydroxide will be a basic hydroxide. If oxide was acidic, hydroxide will be an acidic oxide. If oxide is neutral, then corresponding hydroxide will also be neutral. If oxide is amphoteric, corresponding hydroxide will also be amphoteric. Sir, what are you saying? I'm giving you examples, whatever we have done. Metal form oxides that are basic, so basic oxides. Their hydroxides will also be basic. Non-metal form oxides which are non-metal. Where is non-metal? Okay, non-metal. Non-metal silicon, boron, nitrogen, carbon, non-metal form oxides which are acidic. When goes to water, they form acidic hydroxides. What about amphoteric oxides of generally metalloids? Metalloids we have seen. So these metalloids, these amphoteric oxides, when go to water, form hydroxide. Definitely they'll form hydroxide, but their nature will be of the oxide amphoteric. They'll react with acid also. They will react with base also. Very important conclusion. Moving ahead now. Coming to application of electronegativity, sir, most of the application we have seen, I'm just listing them. Now, the first application says obviously metallic character. Sir, electronegativity decreases down the group. So, electronegativity is gaining of electron. So, electropositivity is giving of electron. So, if electronegativity is decreasing down the group, so electropositive will be increasing. So, metallic character increases down the group because, but decreases along the period because along the period electronegativity increases, so electropositivity will decrease, just the opposite. Okay, I'm using a laser so that when this notes come to you, you can easily, I will not do kachra in that. Moving ahead, bond length. Now, this we have already seen. Let's say I'm H, that person is Cl. If Cl is electronegative, it will attract this shared pair of electron. So I'll be attracted toward him. Bond length will get reduced. So more be the electronegativity difference, more is the difference, lesser will be the bond length. Because in that case, if this hand is attracting the shared pair of electron, then both of them will come closer to each other. And distance between two nucleus is called bond length. So more be the electronegativity difference, lesser is the bond length. Just like HF. HF has, obviously fluorine is most electronegative, so HF bond length will be much smaller. Although fluorine is small, that is also a reason of bond length of HF being small, but because electronegativity difference is also very large, so it will be much reduced. Now, a very important point, acidic strength of hydrides. Sir, what is electronegativity? Ability to gain electron. So let's say if I ask you who is an acid, we know through Bronsted-Arrhenius concept, who give H plus, who will give H plus? You have to take that electron. Who will take that electron? Sir, HF, because fluorine is most electronegative. Then H2O, then NH3. Why? Because fluorine is most, so more be the electronegativity, more is the acidic nature of hydride. Moving ahead. Now, this actually, as I've already told you, see, when electronegativity difference between two atoms is large enough, the more electronegative atom will directly take the electron. So that bond, that molecule will become ionic molecule. And if electronegativity difference is okay, then the bond will remain and it will be known as a polar covalent molecule. Sir, is there some experimental determination that we have reached to this conclusion? Obviously. So this was given by various scientists, Henny and Smith and Gellies. I do not want you to learn this also, although few questions, very few questions are asked that how can you calculate percentage ionic character, 16 into electronegativity difference plus 3.5 into electronegativity difference squared. So whatever value you get, that gives you the ionic percentage. But I'm just giving you a common sense. What is the common sense? Let's say if electronegativity difference between two elements is large, actually the value is 1.7. If it is greater than 1.7, then you will say no, the compound is ionic. And if it is less than 1.7, then you will say it is covalent. Sir, what electronegative scale we use? Generally, Pauling scale is used. So this is a formula of Galli's is more or less, maybe you should learn. You should know. Now, sir, what we will learn? Common sense. Electronegativity difference is large, then I am ionic, small, then I am covalent. Moreover, metal oxides are basic, non-metal oxides are acidic. So let's say if I am going along the period, electronegativity is increasing. And because electronegativity is increasing, therefore, who will be found at the extreme right? Sir, non-metals. Who will be found at the extreme beginning? Sir, metals. Metals oxide are what in nature? Sir, generally they are basic. Non-metal oxides are acidic in nature. So acidic nature of oxide increases along the period and basic nature decreases along the period. So let's say sodium and manganese both are metals. Who will be more basic? The basic nature reduces. Therefore, Na2O will be strong basic, MgO will be basic. Through the properties, through the factual science, we know aluminium is an amphoteric oxide, as it reacts with acid also, base also. So this becomes the borderline. I mean, the midpoint. Above element form acid basic oxides and below form acidic oxides. Acidic nature increases along the period. So silicon is weakly acidic. Moving to the right, phosphorus is acidic, obviously more acidic than silicon. Sulfur is more acidic than phosphorus, and chlorine oxide is very strongly acidic. That's why this Cl2O7 goes to water, form HClO4, a very strong acid. So these are some applications, actual applications of electronegativity which you should know. Now, some people are very confused. Sir, can you, because JEE also asked them a lot of times. This we have done. What is it? As electronegativity increases, acidic strength of oxides and oxoacids. What are oxoacids? Like H2SO4, HNO3, as in an element containing double bond O and has a capacity to give H plus also because it has some OH groups also. So as the electronegativity increases, acidic strength of oxides, oxoacids, all increases. So for example, this is also non-metal, boron is non-metal, carbon is non-metal, nitrogen non-metal. Who is more acidic? Electronegativity. Nitrogen is most electronegative, so it will be more acidic, followed by carbon, and boron will be least acidic, although they all will be acidic because non-metal form acidic oxides. This we have done. People find lot of problem in ticking, because question asks, which of the following is amphoteric? Which of the following is neutral? Neutral do not react with anybody. Neutral oxides, generally there are only 4 you have to learn. Carbon monoxide, water, NO as in nitric oxide, and N2 as in nitrous oxide. These 4 are the neutral oxides which neither react with acid nor with base. Learn them, very famous. CO, water, NO, and nitrous oxide, N2O. Nitrous oxide is also the laughing gas used by dentists. Now, coming to amphoteric oxides. Sir, amphoteric oxides generally metalloid form amphoteric oxide? Generally, yes. Sir, JEE, mains, advanced, all of them love them. So that's why I'm giving you a rhyme for learning amphoteric oxides. What's the rhyme? What's the rhyme? Suno janabe Ali. Suno, jaise you sit in a शेर व शायरी महफिल, तो सुनो जनाबे आली, सुनो जनाबे आली और उनके, I mean जनाबे आली and Lucknow side, some it's a respectable term, जनाबे आली, like you call you Mr. is a prefix used to give respect, so like in Urdu it is जनाबे आली. तो सुनो जनाबे आली और उनके बेकार भाई. सुनो जनाबे आली और कौन सुने? Who else will listen? Their bekar. What is bekar? Of no use. Bekar bhai. और उनके, do not take it personally. I'm just giving you a rhyme. सुनो जनाबे आली और उनके बेकार भाई. Now, they want to listen. What they should listen? You are asking them to watch. Watch what? Watch as in sub TV. Like you say, सुनो जनाबे आली. They will listen to you. They will look at you. So you say, no, watch. So they'll say what? You say as in sub TV. Sub TV is a TV channel. So as in sub TV. Now, why I'm making you learn this time? Very important. Suno Janabe Ali. Suno as in SN. Janabe as in ZN. Ali as in AL. Or unke is nothing. It's just for getting the rhyme. Bekar. Be is beryllium. Kar is chromium. और उनके बेकार. Now who is bhai? Just below these elements, you have to think of those elements. Kashi gaye Shankar Parvati. So below SN you get lead. Zinc, cadmium, mercury, but cadmium just below. Began, alu, gajar, as in beneath aluminium you get gallium. So suno janabe Ali और उनके, there's nothing. Bekar bhai. Who are bhai? Just beneath these 3 elements, whatever element comes. Lead, cadmium and gallium. Now, suno janabe Ali और उनके bekar bhai. Now they are listening to you. What you will say? Watch. They'll say what watch? You'll be humble then. As in sub TV. Watch. They'll say what watch? As in, you will say as in sub TV. Listen, no, as in sub TV. As sub TV. AS is arsenic, SB is antimony, TE is tellurium, V is vanadium. Now, a very important point. Sir, in what oxidation state they are amphoteric? Obviously, sir, this is carbon family, so this will be amphoteric in +2 also, +4 also. We'll see later in chemical bonding why 2 different states become stable, the inert pair effect. We will see in bonding. Zinc and cadmium form oxides which are amphoteric in +2 state. Aluminium, gallium form oxides which are amphoteric in +3 state. Beryllium is an alkaline earth metal, so it forms an amphoteric oxide in +2 state. Chromium forms amphoteric oxide in +3 state. Arsenic, it's nitrogen family. New Zealand, Pakistan, Australia, yes, sub BK. So arsenic and antimony form amphoteric oxides in +3 state. Tellurium, usse tipo, it forms amphoteric oxide in +4 state. inert per effect is applied, +4 is amphoteric, not +6. I'll be discussing the inert per effect in chemical bonding, so don't worry, but till now this you have to learn only. Now, vanadium forms an amphoteric oxide in +5, but I'll give it a different color because it is a controversial thing. Because many times +5 state as in V2O5. Because many times V2O5 reactions can be seen as acidic also. Now, this is just a bit of science that for some scientists have taken, let's say, a sample of 200 reactions of V2O5. Out of those 200 reactions, let's say 130 are acidic. So he will not buy this, no, that it is amphoteric. Somebody has taken 8,000 reactions, and out of those 8,000 reactions, let's say 44,100 is acidic. So 4,100 and 3,900, they'll say no, acid also, base also. So that is a controversy which you mostly find while seeing. I mean, mains is far away from these controversies, so you can take it as amphoteric, but I'm just giving you a caution also that some of the questions take it as acidic. Now, this is amphoteric oxides. Suno janabe Ali और उनके बेकार भाई. When they listen to you, you'll say watch. They'll say what? As in sub TV. You will get the rhyme of those amphoteric oxides. Now, again, what we have said, doing some questions, order of acidic nature. Sulfur, selenium, all the first we'll check the oxidation state. Oxidation state all have +6. Okay. Then this is oxygen family. Say tipo. Down the group electronegativity decreases. Who is most electronegative? Sulfur. So it will be most acidic. I mean, these are just set of problems for you. I've just joined them together. Now, over here, nitrogen, carbon, boron. Oxidation state all are same. First check oxidation state, because more be the oxidation state, more is the electronegativity, more is the acidic nature. So first oxidation state are same. Nitrogen is most electronegative, so HNO3 is most strong acid, we know also. Then chlorine, bromine, iodine. Chlorine is most electronegative, so most acidic. Then sulfur is most electronegative among selenium and tellurium, so most acidic. Then phosphorus, so most acidic. Then nitrogen, phosphorus, arsenic, most acidic, so most electronegative, so most acidic. I mean, these are just similar electronegativity application. Coming to elements having different oxidation states. So when oxidation, more is the oxidation state, more plus, more ability to gain electron. So this is +5 oxidation state of antimony. This is +3. Obviously, +5 is more plus, so more plus is more acidic. Similarly, here chlorine is +7. Here chlorine is +5. Here chlorine is +3. Here chlorine is +1. So more be the positive oxidation state, more is my electronegativity. You can clearly see some more examples. Please do these examples. I mean, I've just listed them together so that many questions of yours will be done. Moving on. Now, some questions. Let us wrap our chapter, because see, I wanted to finish this early, but if you have to combine chapters, time sometimes exceeds. So please bear with me for a few more slides. You have to identify, I mean, these are just previous year PYQs. Identify the correct statement about P block. It is saying non-metal have higher electronegativity than metal. Non-metal have higher electronegativity. Yes, sir. Though this is definitely correct. You have to select the correct statement only. So one is correct. Non-metal have lower ionization enthalpy. Array, this is wrong, sir. Compounds formed between highly reactive non-metal and highly reactive metal. Highly reactive non-metal will try to gain, and highly reactive metal will try to give. So when I want to give, I will give, form a cation. The non-metallic one want to take, so will take and form an anion. So this is also right. And compound will be ionic. Non-metal oxides are generally basic in nature. No, non-metal are acidic in nature. Metal oxides are generally acidic or neutral. Metal oxides are generally basic. So it is written acidic. So this is also wrong. So answer is 1, 3. Now, this is the one question that I'm telling you because these are the theoretical question. That's why I'm discussing so much of theory with you. Another question, XYZ are elements of third period. Oxides are basic. Okay. So if X is basic, then X must be a metal. If Y is amphoteric, then it will be in between metalloid, and it is acidic, so it will be non-metal. Non-metal comes later in the periodic table. So who will have higher atomic number? Z. X will have least atomic number. Y will have an atomic number in between. So X, Y, Z, X, Y, Z, X, Y, Z, X, Y, Z. Simple answer. Now, again, you just have to check electronegativity. Electronegativity increases along the period and decreases down the group. This is the periodicity of electronegativity. Just plot these elements, you will find who has higher, who has lower. Now, some periodic variations. Now, sir, do electronegativity has irregularities? Yes. So, I have listed few points for you. In group 2b, what is 2b? Sir, B as in transition elements. So zinc, cadmium, mercury as in 12th group of our modern periodic table. Zinc, cadmium, value of electronegativity. I'll just put the laser so that I may not, because these notes I'll be giving you, so this will be fresh for you. Value of electronegativity increases down the group. Sir, value of electronegativity down the group, it decreases. For zinc, cadmium, mercury, it is saying it increases. Why? Sir, their Z effective is large. So Z effective is large, so nucleus will be stronger. Nucleus will be stronger, so it will be attracting more electrons. So this is a catch. Some periodic variations apart from the general periodicity, so listed them. So zinc, mercury is actually more electronegative than zinc because Z effective increases. So again, listed whatever exceptions are there, whatever periodicity variations are there. 3A as in 13th group. If you talk of 13th group, the most notorious group, aluminium, gallium, in in size also there was an anomaly, in ionization enthalpy also there was an anomaly. So electronegativity also has an anomaly. Electronegativity of gallium is larger than aluminium. Zero group, they do not have, they have zero tendency, though it is zero. Electronegativity of cesium, francium are equal. Down the group, electronegativity decreases. Cesium is 0.7. Francium is also, over there I have not written because it is radioactive, not generally asked, but the electronegativity of both are equal. Now, what is 2B? Sir, again, it is talking of the zinc, cadmium, mercury. Value of electronegativity. Acha, this has been repeated. So, I'm sorry to remove it. Moving ahead. Now, some other variations in periodic table, left to right. Some basic points about boiling point and melting point. Generally, we will be discussing more about it in chemical bonding, but just to list some few points. If molecules have stronger intermolecular force of attraction, they will be having stronger melting and boiling point. And if it has weaker intermolecular forces of attraction, obviously melting point will be less. Moving ahead. From left to right, boiling point and melting point first increases. First, boiling point increases, then decreases. So, what common sense I am drawing from here? First, it increases. So, we are starting from S block. So, as we move along the period, melting and boiling point increases because obviously the mass increases. So, S block generally has low melting and boiling point in the respective period. That is what I am telling you to learn. Because they crystal structure, solid state have got out of picture. Actually, the crystal that they form is not that strong. It forms a body-centered cubic crystal, alkali metals. Therefore, they have low value of melting and boiling point. While transition metals, we have moved along the period, so they have attained a maxima because their atomic solid structure is face-centered cubic. You just learn that they have very good, very solid, very awesome solid structure. Solid structure, if awesome, then melting and boiling point will be high. So they have high melting and boiling point. Inert gases, obviously they are gases, so they have lowest. So transition have highest. Inert gases have not even there in the picture, gases, and alkali metal have lowest if you compare solids, because alkali metals are also metals. Alkaline transition metals are also metals. So transition metals have high melting and boiling point. Alkali metals have low melting and boiling point. Among them, tungsten has highest melting point. Value you should leave, but you should remember this. Tungsten is the highest melting point metal and mercury is the lowest melting metal. Some other points. As we know, melting and boiling point for alkali metals, for S block element, melting point, boiling point, if you go down the group, it decreases. If you go down the group, it decreases. Why, sir? Mass increases. See, alkali metal, actually for metals, the valence electron forms their metallic bond. So for let's say for alkali metal, how many metallic bond they form, sir? The number of valence electron they have. What is the number of valence electron alkali metal has? Let's say, sir, this is lithium and this is lithium. Because it has one valence electron, so it will be tied up by one metallic bond. Let us come down. This is cesium and this is cesium, but cesium also has one valence electron, so it is also tied up by one metallic bond. Sir, two small cats are tied by a rope. They will be stuck. Two large elephants are tied by the same rope. They will just do the rope and rope will break. So actually, this one metallic bond is sufficient to hold these small atoms, but this one metallic bond is not sufficient to hold these large atoms. Therefore, for alkali metals, when we go down the group, melting and boiling point both decreases. Very, very important point, because S block, P block, I'm skipping. So I'm taking their logics over here. That's why lithium and sodium in room temperature are solid, whereas cesium and francium are liquid. Now, it is due to weak energy and metallic bond, which I have already discussed. Now, in D block element, boiling and melting point increases down the group. The boiling and melting point in D block element, in S block element it is decreasing, but in D block it is saying that it is increasing. Why increasing? Because their nucleus is quite strong, and if nucleus is strong, so the metallic bond that the nucleus will be forcing those electrons to form will also be strong. Moreover, in D block element they have more number of valence electrons. Actually, the unpaired electrons are responsible for forming the metallic bond. So because they'll having more number of unpaired electrons, so they'll be having more number of metallic bonds. More metallic bonds are formed. That means two solids are held together more tightly. So if held together more tightly, melting and boiling point will be large, and down the group it increases also. This you have to learn. Now, some other variation from 3A to 4A, that is, we are talking of P block element, boiling point and melting point decreases down the group. And from 5A, that is from nitrogen family till 0 group, boiling point and melting point increases down the group. This you have to learn, that we have read this, no? Boiling point and melting point decreases. So this decreasing thing takes place till what? Till 4A, as in 14 group, as in carbon family. From nitrogen family, you can learn the common sense. What from nitrogen family till inert gases, what is the trend? 10 kilo will be boiled at high temperature of 1 kilo. So 10 kilo. So as mass increases, boiling point and melting point increases. But this common sense is valid after group 15. Till group 14, that S block trend is followed. That is, down the group, melting and boiling point decreases. Actually, it has got some application of inert pair effect also. We'll be discussing in chemical bonding. But this much you have to learn here only. Now, melting point and boiling point of monoatomic molecules are less, while diatomic molecules are large. For example, inert gases are monoatomic, halogens are diatomic. So, inert gases have less melting and boiling point because monoatomic molecule will be less. So, the small molecule will have small attraction forces. Relatively large molecule will have large attraction forces. What attraction forces? Non-polar molecules are attracted by van der Waals forces of attraction, London dispersion forces. So, more be the surface area, more is the attraction. Therefore, diatomic molecules have relatively high melting and boiling point than monatomic, as in inert gases. Atomic solid, okay, now there are some non-metals also which exist in solid state. Only metal does not form solid. Actually, covalent solids are also formed, like carbon. Diamond is not an ionic solid, it is a covalent solid. So there are some non-metals which can form very strong, very famous covalent solids like boron, carbon, silicon, and they have very high melting and boiling point. But the bond that they are attached with is not metallic bond. It is strong covalent bonds. So as you can clearly see, bond is coming in our explanation in our statement, because obviously the next chapter will be chemical bonding. So this is me, Gaurav Singh Arora, signing off. Periodic table we have done, but your job will be done when you will be practicing questions. Most of the PYQs I have given. Rest of them will be there in the sheet or maybe your PYQ sheet, so you can download it from the PW app, the link to which is given in the description section. So this is Gaurav Singh Arora again, signing off for now.